That was a beautiful speech. Thank you, sir. Next in line, we have Dr. K.R. Murli Mohan. He has been part of the Department of Science and Technology from 1998 onwards, and presently he is the Mission Director, Interdisciplinary Cyber-Physical Systems and Scientistry, and heads the Frontier and Futuristic Technology Division. Also, he is working on the development of National Mission on Quantum Technologies and Application. It is an honor for me to call upon Dr. Murli Mohan to enlighten us with few words. Dr. Mohan, can you step up and address the gathering?
Thank you, Diksha. And I thank Professor Chaudhary, Kamath, and other Subhasish who invited me for this great occasion. I thank you one and all. Well, nicely, Subhasish has elaborated, the spectrum of, this particular conference. And Dr. Chaudhary elaborated, the institutional preparedness and his vision for the institute, and then the type of activities he has initiated as IIT Jodhpur. I would like to bring in, the governmental perspective in the whole thing. Before getting into that, I have some fundamental observations. Maybe this conference will come out with a tangible type of outcomes. Well, we are in the digital space, started with the Alan Turing mission, and we evolved to this particular stage. We have silicon-based or a digital revolution, which brought in computation, the communication, the sensors, the secure communication. So many things we evolved over the period of 60, 70 years. We, in the sense, the total world, say. Then these things are evolving and still evolving. Now, suddenly the quantum, technologies come into picture. And what we have done till now in the digital space, we try to replicate in the quantum domain also. So either you call it as quantum computing, quantum communication, or secure communication like UKD, or quantum-based sensors development or devices. So whatever we have done in the silicon space, we are trying to replicate in the quantum space as well. Why? That is an important question. And why the total world is concentrating on quantum technologies. And so much of investments and intellectuals are aggregating and developing these technologies in the quantum space is a very interesting point to be discussed. So definitely there is an advantage in the entire. Well, in the process, in the silicon space, India has advantages and India has had certain lacunas also. For example, in the sphere of the computation, the fabrication or development of the hardware, somehow we are lagging behind. But we pick it up very fast in the software domain, and we are the force to reckon with in the area of software. But here is the new opportunity which is coming and knocking at our doors in the areas of quantum technologies and applications, both in terms of development of hardware, both in terms of the applications development, and both in terms of the new technologies based on quantum sciences is an opportunity for us. We have to reaffirm, and what we have done in the silicon space, probably that is a learning for us. We may have to reinvent ourselves and grab this opportunity, and probably we can convert this entire ecosystem into a type of meeting our own requirements, governmental requirements, and as well as industry, plus connecting to the government vision of 5 trillion economy. There is a huge opportunities for us. Well, these are the various opportunities available in front of us. Then what we have to do, or what we can do, or what government is doing is very important. So I will dwell upon what government is doing, particularly Department of Science and Technology. So DST recognized quantum technology as a very potential and emerging area way back in 2016-17 itself. Though there are a lot of research going on in silos and as well as in isolated places, we are able to bring all the researchers onto a type of a platform as an R&D platform. We call it as Quantum Enabled Science and Technology R&D Initiative. Something like around 180 or 186 crores has been funded for this, and we aggregated something like 55 researchers, very good with background, and as well as young people uh, who are aggregated and then working towards the R&D ecosystem and augmentation. That program is also not only for R&D, it is also for generating human resources also in terms of PhDs, because this field has to improve means we need to increase in the number of researchers in this field. So that is one of the basic idea of the quest. Now the program is up and running, and most of the researchers of quest are available in this particular conference, and they will be sharing their ideas and as well as the research results. And we are very comfortable with this quest group, and it is doing a fantastic job, and we hope it will continue. Then next point, where the DST involved is, as part of the cyber physical system mission, an innovation hub on quantum technology was initiated at Indian Institute of Science and Education Research, Pune, ISAR Pune. That particular hub is dedicated for quantum technologies. One hub is there already in IIT Jodhpur. You know the structure of this innovation hub, and the structure, the freedom and flexibility, the operating freedom, everything Similar structure has been created in quantum technology at ISAR Pune, and probably they also will be participating, and they will be sharing more details about that particular innovation hub. That is the second thing. The third aspect is government is also announced a huge national mission on quantum technologies and application. It was mentioned in the budget also. And the DST is in the process of launching. The process initiated, and probably maybe another 3 to 4 months period, we will be able to hear about the quantum mission. That is also a huge mission, wherein all the stakeholder ministries like Department of Space, Atomic Energy, DRDO, and other stakeholders, ministries are all part of it. So it is an interministerial, interdepartmental mission coordinated by Department of Science and Technology, wherein the three helix, Professor Chaudhary mentioned about the academia, industry, and as well as the government coming together and launching this mission towards a set of goals and objectives. Probably a development of a quantum computer may not be general purpose. It may be a processor development and working on other devices. Also development of the free space and as well as fiber-based quantum communication, and development of the QPD systems. And also the main part of this particular mission will be on working on developing sensors, quantum sensors. And of course, the other peripheral devices like registers, memories, and those things also will be part of the entire mission. Therefore, there is a clear-cut goal and objective, and we have the internal capacities, to address these, research issues, and the mission is aiming at that. We are all aware that the quantum research is equipment intensive. Huge infrastructure is required to carry out the research. So therefore, government recognized that particular aspect, augmenting the huge infrastructure established in India, so that we will have a better platform to work on development of the technologies. So not only development, it is the deployment also. So we have our internal systems, both the defense, civilian, and as well as the security applications. So there are very financial systems which require this type of technologies. So these are the things that the mission is planning. Now, it is truly interdisciplinary systems, because the physicist, the chemist, the material scientist, the electronic engineers, the computer scientists have to come together. It is the domain of not only the physicist, but it is the domain of engineers. So here, the main challenge is the physicist and the engineers have to come together to build the rapidly the prototypes and the systems. One is the theoretical development, the experimentation, and then the converting that total results into a workable models. Unless otherwise the engineers are not involved, it may not be possible. So therefore, it is truly multi-departmental and multidisciplinary, and as well as a object-oriented type of activity. And we have to re-up this opportunity. We have to come together and then work towards development of this technology for the benefit of the country and benefit of the world. So we are, the government is ready. I know academics also ready and the industry is also ready. So therefore, here is the platform for us to come together and work towards these particular ambitious projects that government is intended to implement. I thank for this opportunity. I would like to listen from other people. Thank you.
Thank you, sir, for your wise words. You have brought several important points to our purview. It is truly a blessing to have you here. We will now move on to our final inaugural speaker, Dr. Sudhir Kamath, to deliver the first plenary talk of the conference. Dr. Sudhir Kamath joined Microwave Tube Research and Development Center, DRDO, as Scientist B in 1985 and took over as the director in 2015. There he has handled various responsibilities as project manager, group head, divisional head, and project director of the years and over the years and has contributed to a number of projects and technologies for development of microwave tubes. Now he is the Director General of Microelectronic Devices, Computation Systems, and Cyber Systems. He has received DRDO Scientist of the Year award for his significant contribution in the field of microwave tubes. He is also recipient of the DRDO Agni Award for Self-Reliance twice. With that, I would like to call upon Dr. Kamath to kindly unmute himself.
Thank you. Thank you very much, Diksha. Professor Shantanu Chaudhary, Director, IIT Jodhpur. Dr. Murli Mohanji, who is of course well-known figure on the quantum technology side. Professor Banerjee, eminent speakers and participants of this particular conference, which is online, quantum information and computation. And what is very interesting is from fundamental to applications. That is what is very important. Of course, my job has been made simple by earlier speakers. Professor Chaudhary, I think I should also compliment you for taking this initiative of quantum technologies in IIT Jodhpur, as you said, in 2019. And I was very happy to also know that IBM has also recognized IIT Jodhpur as one of the centers for quantum technologies from their side, and which is a good news. And I'm sure the students and the researchers in your institute and in India will definitely get benefited from this collaboration. Now, coming to Professor Mohan has already given a very good bird's eye view about what are the various initiatives taken by government on quantum technology. As it is very well known that quantum physics is nothing new. It is well-known things for maybe more than 50 to 100 years. But applying it, trying to use it as a technology or for the information technology side, this is what is new. And as it has been said by the speakers, that is where the various domains or various fields of engineering, not only engineering, but also the physicists are also have to work together along with the industry. Why is required? Because generally, when we talk about physicists, maybe I think they generally go and tend towards working deeper into the physics side, but somewhere in the process, because their focus is to go and find out new physical phenomena or new processes. I mean, they are not having enough time probably take it forward to the application side, and that is where the engineering field comes into play. And engineering field, various engineering domains actually have to work to make a product, and of course to commercialize it, industry is required. And all of this seems to be happening at present very vibrantly in our country also. As it has been already stated, the government has taken the initiatives and also already declared this decade will be the quantum decade, and that is how I think this announcement was made last year for the quantum technology budget. And a program like NMQTA, which has been already led by Dr. Murli, is known to all of us, and where number of participants, like various IITs, IIC, and ICERs are coming together with other research institutes. They are doing a lot of good work on the theoretical side as well as fundamental research side. Of course, as we all know, to carry out the real meaningful and futuristic research, and as it has been stated by the Prime Minister, Honorable Prime Minister, that I think that India has been always technology chaser, but now it is time has come that we should do something to be a technology leader. And that is where I think all these three domain of field of domain people should come together and work to see that India definitely don't miss out like in other technologies earlier, and be a leader in quantum technology. Now coming to the DRDO's perspective, DRDO, as you all know, we are working for the defense applications, various requirements, and that is where, if you say quantum technology, there, as you all know, there are four major domains in the quantum technologies: quantum computing, and you have quantum communication, quantum sensors, and quantum materials. Now, all these four of them are very important for defense application. And keeping that in mind, all of you know that DRDO has also taken initiative. We have made a roadmap for next 10 years as to which are the areas where we need to work, where the requirement of defense can be met, apart from commercial and various other applications. And we also have been working in a smaller way. Now, a new lab has been formed with the younger scientists because they have a futuristic vision. The Young Scientist Lab on quantum technology specifically has been formed, closely working with KFR and other R&D institutes in a smaller way to develop a few qubit quantum computer, which is in the initial testing stage, and most likely, if everything goes well, probably this also can be made successfully, and it can be probably made available for the students for use sometimes next year. As you all know that this is only a baby step, and this can be taken forward by the NMQTA program with the CDAC, who are taking in a big way the quantum computing side, where all these agencies, including the DRDO lab, will collaborate and try to see whether the high-level quantum computing facility can be made available. Right? While saying so, I think we should also thank CDAC and MIT for providing the quantum simulators, which is already been available now for the students to carry out various development of algorithms or play around with basic algorithms for when the quantum computer comes. That is one part of it. The second domain, which is quantum communication, which is most important as a secure communication. And you all know that the defense lies on secure communications.
Larry.
Hello? Yeah. Okay, I think some mic may be on. So I think when it comes to secure communication, most important thing is the quantum QRNG, that is quantum random number generation, or quantum communication, or QKD, quantum key distribution. Now, here I think you all know that we have taken some initiative, and last year we have already tested a QKD up to 10 kilometers, and at present we are in the process and try to demonstrate up to and beyond 100 kilometers of quantum QKD, that is key distribution, as well as the quantum random number generation generator also has been designed and made, which has been demonstrated, and now we are trying to also use them in a initial stage, because any secure communication purpose, there is certification requirement is there, and that up to some extent we could achieve it, but right now for that again the framework need to be brought in place, for which the other lab of DRDO is working on that. And once these frameworks are ready and we also qualify that it is really secure, then I think using the QRNG developed within the country, we can also develop the necessary random keys which is required for secure communication. And the key distribution over the wire also can be initially initiated because already we have demonstrated to some extent. Now we are trying to implement it in some of the critical areas so that we need not have the conventional way of distributing these. Now coming to third domain is that enough? That can we go beyond 100 kilometers? Because as you know, the losses in the fiber is too high, and as the losses go high, actually we will not be able to communicate. The quantum photons cannot travel that distance, and that is where I think we need to change the mode. And we are now also looking at, because as you know that developed countries like US and China has already demonstrated the quantum key distribution through satellite. That is another task, futuristic task we need to work upon, and that will be a real challenging job, because it is not only the launching of satellite or pointing and tracking point, which is very important, but also the hardware which is required to be placed in the satellite, and also ensure that it is really secured and safe distribution of keys are possible. And you know that when we demonstrate initially, of course, the key rates are not very important, but definitely unless we improve upon that, the formal quantum communication, whether it is audio or video, is not possible. And that is where the speed of communication need to also be improved, and a lot of work need to be done. Right now, it is only in the nascent stage. There are other sensors. The third vertical is on the sensors. Number of sensors are actually available, being discussed, but theoretically it is possible. Some of the places the experiments are being done at some of the institutes as well as R&D centers. But what is very important is like quantum clock, or maybe the quantum magnetometer and quantum gravimeter, and such sensors are going to be useful or very important for particularly defense application, where we need to use it for a number of strategic applications. I need not dwell upon that. The literature is available where all these things are talked about. Now, apart from that, we are also looking forward. When we need to work on sensors, it is very important to work on quantum materials or various processes required to be developed to make these sensors and make these sensors more reliable and useful for the system. Now, once we develop all these things, now the main important area of work for the defense is the quantum radar or quantum imaging. Now, these are the two areas which, of course, people have been working, but still, I think it has not come to mature to a stage or level where people can demonstrate very effectively a quantum radar. Now, this is one of the area where I think, you know, that last year we have already declared the number of list of product which we are able to now in the country make ourselves. Radar systems are one of them, which is apart from missiles and other things. Radar is right now said that it is whatever futuristic radar requirement is there can be developed or is available in the country, and we need not import. That is using the conventional technology. But now we are talking about quantum radar. I think it is time that we should start seriously working in this area, domain of work, and prove the basic concept, and then try to realize it in the form where it can be used for the military purposes. And that is very important job, because first of all, the prototype demonstration itself is a tough task, and later on getting it qualified for the military purpose is another challenge which need to go we need to go through. And we have time, but of course we cannot lay back and then wait for other technologies to come up. We have to start working, and request academia and industry along with the R&D institutes to come together to work toward this area, and which we are serious about doing this. Now, these are the various domains right now we are focusing, but at the same time, it is very important that the knowledge of quantum technology, the importance of quantum technology need to be, the awareness on this need to be created. As you know that right now, number of agencies are working. I will not say in silos, but they have been collaborating together. But NMQTA program, most likely, which has been initiated by DST, is going to bring academia, R&D institute, and the industry together to bring out this level of quantum technology to some level where probably the products will start coming. And at the same time, it is important the basic the uh, the manpower or the knowledge base should also be created. And I once again would like to compliment Professor Chaudhary, Shantanu Chaudhary ji, for taking this initiative, making a hub there in IIT Jodhpur, and also taking a wonderful initiative in this in the form of this conference for quantum information and computation. I'm sure I could see that unlike other conferences which stretches to only 2 or 3 days, it is for 5 days, and that means it is really exhaustive. And I saw the various the expert speakers. There are speakers, international renowned speakers, theoreticians who are talking about various domains and fields. There are researchers as well as the industry meet, and as you said that there will be a panel discussion. I'm sure with all this at the end of 5th day, we will be better educated and better known to have a particular direction which we should progress. And also IIT Jodhpur will take a lead in this direction. All the best, and thank you very much for inviting me to this particular.
Thank you, sir, for discussing the state of quantum research going on in India. We have come to the end of our inaugural session, and we have few minutes before we dive headfirst into obscure waters of quantum mechanics, where our invited speakers will show us the way. Okay.
Let me also formally thank Dr. Kamath and Dr. Mulli for gracing the inaugural session. Thanks a lot, and thanks to the all organizers and others who have participated in the inaugural session. Thanks.
Thank you. All the best wishes for this conference.
Thank you. Thank you very much.
Now we will meet at 3 p.m. Please join at 3 p.m. again.
Can anybody hear me? This is Michael Hall.
His PhD in 1989, and he has held several distinguished positions since then. And he's a prolific worker. He's published several books on quantum mechanics and general relativity. And he has done some very path-breaking works on quantum information and open quantum systems. And today he's going to speak on recycling of qubits for sequential sharing of Bell non-locality. So without much further ado, I would like to welcome Professor Hall. And your talk is of 1 hour duration, and I hope you will leave some time towards the end for questions. So Professor Hall.
Thank you very much, Professor Majumdar. I'll just share my screen. Can you see my screen okay?
It's just about coming, I think. Just wait for a moment.
Okay, let me go down a page.
Yeah, I can see yeah, now I can see it. Yeah, fantastic. Yeah, please go ahead. Yes, yes.
Terrific. Okay, well, thank you very much for the introduction, and also to the organizers for the invitation to speak. It's nice to be overseas, at least in a virtual sense, where it's being so difficult to travel. So I'm talking to you from Canberra, Australia, and it's 8:30 in the evening. My hair might look a bit messy because we've just come out of lockdown on Friday after 9 weeks, and I haven't been to a hairdresser yet, so I apologize. This diagram you're going to be seeing a lot of during the talk. It shows a source and it shows some agents making measurements. And the traditional name for these agents, of course, is Alice and Bob, maybe with some subscripts. But in this case, I can actually introduce who the agents are that helped you bring this talk. There's Xiuming Cheng, an ex-PhD student of mine in Shanghai in India. His wife, Li Jin Lu, at the moment living in a different city in China. Travis Baker, who's just finished his PhD with Howard Wiseman up in Brisbane, Australia, and myself in Canberra, and which is Canberra, for those who don't know, is to the west of Sydney, about 200 kilometres in southern Australia. Okay, and you'll see that Xiuming's holding a baby. So he and Li Jun, just 2 weeks ago, became parents for the second time. But of course, I'll be talking about what the four of us have produced as academic parents. And that's in these two e-prints showing down the bottom. So the outline of the talk, I understand there's a lot of students attending the conference. And so I'll start off fairly gently and just review some ideas about what is called Bell non-locality and the Clauser-Horn-Schimmeny-Holt Bell inequality, and why they're interesting and useful. And then I'll go on to this truncated diagram here. You can see I've got a quantum network with a source and only 3 agents this time. And we're interested in the question, if the source emits, say, a qubit to Alice 1 and a qubit to Bob 1, and they can establish they share a useful quantum resource by measuring their correlations, is there enough of that resource left over that Bob 1 can then subsequently pass his qubit onto Bob 2, and then Alice 1 and Bob 2 have a useful resource to share? Or does all the resource get used up by Bob 1? So this is the idea of recycling that qubit on the right-hand side to sequentially share a resource like Bell non-locality. And the answer is yes, that can be done. But you can go on and ask then, well, that's one side. What if we've got 2 Alices as well? If Alice 1 and Bob 1 can make use of the resource emitted by the source, and then each passes their qubit on, Alice 1 to Alice 2, Bob 1 to Bob 2, can Alice 2 and Bob 2 now share a resource like Bell non-locality? And it turns out the answer to that, was the subject of our research this year. Since late last year, we can't give a definitive answer other than numerically it's fairly definitive. Analytically, we only have a few results. So we have a conjecture that it can't be done. You can't have 2-sided recycling. That's a phenomenon, at least for this particular type of Bell non-locality using qubits. So we call that one-sided monogamy. And I'll present some analytic results, one-sided monogamy relations, as well as some numerical evidence. All right, so I won't spend long on this slide because even students have heard of entanglement. So entanglement just corresponds to having a quantum system in the ideal case in a superposition of 2 or more separated systems, say a qubit over here with spin up and a qubit over there in Jodhpur with spin down, and the converse situation, spin down here in Canberra, spin up in Jodhpur. And you get some strange effects. You get quantum teleportation, you get quantum steering. If you've got a quantum computer based on qubits to factorize your primes very quickly, those qubits have to be entangled, or you have to make entangled measurements. And then there's a particularly strong form of entanglement called Bell non-locality. It first came to be of interest for people in the foundations because it ruled out explaining quantum mechanics by theories called local hidden variable theories. Said it couldn't be done. Some people said that's interesting. Other people said no, it wasn't. And it wasn't until that was in the 60s that got started, but Bell non-locality. But then it was realized essentially in the 90s that, hey, this is not only weird for the people in foundations, but it's actually useful. You can do quantum cryptography where you can generate a secure key that's provably secure with very few assumptions about the laws of physics. You can generate random numbers and guarantee that those numbers are random using the laws of physics. And I'll talk a little bit about quantum cryptography, again, for those without much background in this field. And Bell non-locality is what this talk is all about. Right, so let's talk about Bell locality first, and then we'll go on to Bell non-locality. So again, a cut down version of our full diagram. There's a source, it's emitting a system to Alice 1, another system to Bob 1. Each time you run the experiment, you push a button, that's what happens. So Alice 1, she's going to make one of two possible measurements, x or x prime, and get out a result, x or x prime accordingly, and we'll assume those results are labelled by plus or minus 1. Bob 1, with his system, same idea. He'll choose one of two possible measurements he can make, y or y prime, gets out results little y prime, but always plus or minus 1. So if they're running this experiment on many runs, sometimes Alice will choose x and Bob will choose y. That's a particular joint measurement that they make on those on a subset of runs. And they can collect their statistics and they can say, all right, well, let's multiply for each of those runs the outcome of x by the outcome of y, and we'll average over those runs. You get a number. Similarly, if Alice happened to measure x prime instead on some runs while Bob measured y, you've got a different joint measurement and you can calculate a different average, and so on for each of the four possibilities. So now you have some numbers. Alice and Bob know quantum mechanics. They might try and use that to explain those numbers, but the idea is in physics we want to explain outcomes of measurements. And there's a very interesting class of explanations called local hidden variable models. First defined clearly by John Bell. And what they do is say everything underneath is deterministic and local. So in particular, what characterizes these models is there's a parameter lambda. And if you know that parameter lambda, you know what the outcomes of any of these measurements are. No matter which one Alice and Bob makes, it's predetermined what the answer is going to be. X is some function of lambda, the outcome of x prime is a function of lambda, and so on. And the way the model explains the averages that you see, it just says, well, lambda source emits a different lambda each time. A particular source has a probability distribution for emitting given certain values of lambda. And so to work out the average of x times y, you just take an average over those hidden variables. You take the statistical average over lambda after multiplying the predetermined values together. Right, so and these models are very natural in a lot of circumstances, particularly trying to understand physics in a local and deterministic way. And the set of such models aren't completely general. They can't describe all correlations. They place constraints on them. And this is one of them. Suppose Alice 1 and Bob 1 have measured all these four quantities, then they can certainly add up the first three and subtract the last one. They've measured a number. And that number, if it's been generated or is explainable by a local hidden variable model, has to come out to be no greater than 2. And so that's called the CHSH, Bell inequality. Bell gave the first example of an inequality that local hidden variable models have to explain in 1964. Clauser, Horn, Shimony, and Holt gave one that was experimentally more useful in 1969, and it's the one that's most commonly tested in experiments. Whoops, let me go back. Right, so we have that inequality. So, and of course, the interesting thing is quantum mechanics predicts nature is not Bell local. Quantum mechanics is not Bell local, they're Bell non-local. So here's the inequality written down again, just a sum and difference of some measurable correlations. And it's got to be less than 2 if there's a local hidden explanation. But quantum mechanics says, no, it can be 40% bigger. It can have a value up to 2 root 2. So quantum mechanics is certainly Bell non-local by that definition. Some people just like to say quantum mechanics is non-local. That's a dangerous thing to do. I always put the Bell in front. Okay, but maybe quantum mechanics is wrong. You've got to do an experiment and that'd be a big thing if quantum mechanics is wrong. It's very hard to do a good experiment. And it really wasn't until the 80s that Alan Aspect caught people's attention, and there's been many experiments done since. And these experiments come up with values. This parameter here, the CHSH parameter, comes out bigger than 2, and in some cases very close to this 2√2. And quantum mechanics is always verified. There are loopholes in running such experiments. Typically, for example, you might not detect every run. You may miss some of your qubits, and perhaps that's you haven't got a proper sampling of the statistics. But you can overcome nearly all these loopholes, and people did that very convincingly in 2015. And so we can conclude that not only is quantum mechanics Bell local, but experiment shows nature really is Bell non-local. Okay, so that's nice for foundations. It tells us something about how we can model things. But then, as I mentioned earlier, it turns out to be useful. If you want to generate secure cryptographic key or certifiably random numbers, Bell non-locality is your friend. It's a useful resource. And there's going to be talks later in this conference, which will talk about quantum cryptography in particular. I just want to give a simple one-slide introduction of quantum cryptography, again, for those students. It's time for that, who aren't that familiar with the concept. Now, how does it work? Very roughly, I've drawn the same figure as before, but I should have put in more measurement choices for Alice 1 and Bob 1. Pretend they're there so that Alice might be able to measure X or X prime or X double prime and so on. She's got some set of measurements to choose from. And Bob's got some set, Y or Y prime or Y double prime and so on. And those measurements will have results plus or minus 1. That's the scenario that we're working in. And they can get statistics. And we further assume now, assuming quantum mechanics is correct, our source is a 2-qubit state, maximally entangled. In fact, it's a singlet state. So the statistics are perfectly anti-correlated in a sense I will explain. On each run, we assume that Alice 1 chooses, I'll just call her Alice for this slide. Alice chooses from her set of results at random, her set of possible measurements at random. Bob chooses from his set of results at random. And some of those measurement directions in the two sets are taken to be, sometimes they're equal. They choose to measure in the same direction. It might be the spin up direction, the spin sideways, the spin into the screen or out of the screen, I guess, for you guys. Sometimes they'll choose to measure in the same directions. And the wonderful property of a singlet state is when they do that, their answers are perfectly correlated. They can only get a plus and a minus result. If Alice gets a plus result, Bob gets a minus result. If Bob gets a minus result, Alice gets a plus result. So on those particular runs where later they compare notes and find that they've measured in the same direction, for those runs, they know their results are either plus minus or minus plus. Excellent. Perfect correlations. They can use that to construct a cryptographic key. That's just a sequence of binary digits that you use to code messages. And so the key, we can just say if the plus minus happens on those runs, they decide that corresponds to key bit 0. If they get a minus plus, that's a key bit of 1. So on these runs, the first run they got a 0. Second time they measured in the same direction, whatever direction that was. They got a 1. They got a 1 again, then a 0, and so on. They can make that key as long as they want. And the good thing about it is Alice knows that this key bit is a 0 because she's got a plus. Alice and Bob knows it's a 0 because he got a minus. So whenever Alice gets a plus and Bob gets a minus, that's a 0. So they each independently know what the key is from the measurements that they've made without telling people what the measurement results were. Alice doesn't have to know Bob's measurement result because there's perfect correlation. So she doesn't have to send any signal that can be intercepted by an eavesdropper. Further, and then this is the tricky bit where Bell non-locality is useful. Other times, some of the runs of the experiment, they'll have chosen different measurement directions. And then they can compare their results in those cases for a subset of them and see what happens. And if it turns out that for some subset of results where they've chosen different directions, it's possible that they will find, because they're sharing a signet state, the value of this number, the CHSH parameter, can be very close to 2 root 2. And it can certainly come out to be bigger than 2. And what does that tell them? It tells them their key that they've generated is secret. There's 2 minor loopholes, which I won't go into detail. You have to assume there's nothing faster than light happening between Alice and Bob when they make their measurements. And you have to assume that the source acts independently of the choices. Alice 1 can make her choice of what she's going to choose to measure, x, x prime, x double prime, completely independently of what the source happens to be doing. She can make that choice, or she's got a good random number generator. So under those 2 assumptions, and the fact that you've violated a Bell inequality, there's only one thing that can give. You can't have predetermined values. There's no local hidden variable model explaining their results and explaining their key. And again, you say, how does that matter? Well, it matters because if Eve, our eavesdropper, has access to the true local hidden variable model to explain them, if there was one, then by knowing the hidden variables, she knows Alice's and Bob's results. Therefore, no matter what they measure, therefore she knows the key. But if we can rule out local hidden variable models, then there's no such list that Eve can hold, no such model to tell her what the answers are. And Eve can be anyone outside the labs of Alice and Bob. Nobody knows, only Alice and Bob. So the key's secret. And you can generalize that to where you have noisy measurements, imperfect states, not necessarily qubits, and so on. The greater you violate a Bell inequality by, the higher the rate of secret key you can generate. Right, so that's really just to give a flavour of how Bell non-locality is useful, something worth studying in these days of application. Okay, so here's something very applied, a quantum network. And there's going to be talks on these too. Dr. Sarkar, I noticed, and also Alok Pan, a friend of mine's going to be giving a talk later in the week too. Oops, let's come back. So in a quantum network, you have nodes where maybe there's sources, there's people making measurements at some nodes. They might be generating quantum information, storing it, or they might be transmitting quantum information or classical signals. And this is my go-to node for this talk. And in particular, I'm going to assume there's a source generating 2 qubits. One goes to Alice 1, one goes to Bob 2. And I'm interested in Bell non-locality, and I'm interested particularly in the Clauser-Horn-Schiminy-Holt, the CHSH inequality. So let us suppose, let's look at the following question. If Alice 1 and Bob 1 can use this source in their network to generate Bell non-locality, and then perhaps use it for cryptography or to generate random numbers safely, can Bob 1 pass on his qubit afterwards to Bob 2, and then Alice 1 and Bob 2? Bob 2 makes suitable measurements, and they violate the CHS inequality too. So they're sharing a useful resource. And then maybe Bob 2 will pass it on to Bob 3 and so on. So that's one question. Can you recycle Bob 1's qubit? The answer is yes, as I previewed in the outline. And then what about if Alice 1 also passes on her qubit? Can it be successfully recycled as well? So that not only do Alice 1 and Bob 1 violate the Bell inequality, but so do Alice 2 and Bob 2. And that's where our conjecture is they cannot, not in this scenario. Right. So first, what are the known results? The known results are for that one-sided case, actually. No, that's not quite true. Let me backtrack. There's some known results going back quite a way, actually. And there's 2 fundamental scenarios in this regard. The first scenario is our observers aren't independent. All the nodes of our quantum network are trusted. The observers like each other, they trust each other, and they're happy to share their measurement results and use that to get something interesting out. And so in that scenario, there are a couple of interesting results. For example, it can be the case that the source emits a state which has a local hidden variable model. It's entangled, but not Bell non-local. There's no way that Alice 1 and Bob 1 can violate a Bell inequality. They can test an entanglement witness if they want, but they can't violate the CHSH inequality. So for such a state, though, it turns out, as shown by Popescu in 95, if Alice 1 and Bob 1 make certain measurements and then pass on their qubits to Bob 2 and Alice 2, and they also pass on their measurement results, then Alice 2 and Bob 2 can choose measurements appropriately such that a Bell inequality is violated. And that's called hidden non-locality, because there's no Bell non-locality that's apparent here. Alice 1 and Bob 1 can't see it no matter what they do. But if they do make certain measurements, then Alice 2 and Bob 2 can generate Bell non-locality. So that's quite remarkable. That's called hidden non-locality. That's one interesting thing. Another one is if they're all working together more generally, and so Alice 2 measures some observable W, say, and Alice 1 measures X, Bob measures Y, Bob 2 measures Z. Over many runs, they can generate the joint distribution of outcomes for those settings. They can generate the joint outcomes for other settings. And by sharing those results, you can then test, are these explainable, these joint distributions by a local hidden variable model? Or do they violate higher order Bell inequalities? And indeed, they can violate those inequalities. So there's this higher order networked non-locality some speakers will be talking about. And that's just an example of a paper here by Gallego and others. Right, that's the first scenario. Again, that's not what we're interested in. We're interested in the case where perhaps the different nodes don't trust each other necessarily. They're not going to pass on their measurement results. For example, if Bob 1 doesn't trust Bob 2, Bob 2 might be effectively an eavesdropper then. If Bob 1 tells him what his result was, Bob 2 will say, aha, I'll just measure the same observables. I'll be able to generate, I'll know, I will know the code set up between Alice 1 and Bob 1 that they generate using Bell non-locality. Bob 1 doesn't want that to happen, so he's not going to share any measurement results. What he is willing to do is share his qubit and keep his results secret. And similarly, Alice 1's happy to pass on her qubit, but no results, and so on all the way along. So in this case, we have independent observers on a quantum network. In that situation, what can we do? And again, there's some interesting things. In that first case of one-sided recycling, Bob passes on his qubit. And the observers are now independent. Well, it turns out if Alice 1 can violate CHS inequality, a Bell inequality with Bob 1, but also violate one with Bob 2, even though it's been measured and some quantum information has been lost, there's enough non-locality left to do that. That was shown by Silver et al., Nicholas Gisan, and some other people in 2015. See, this is possible. They can both violate it with Alice, Bob 1 and Bob 2. And it turns out this sort of one-sided recycling is useful. It actually adds an advantage in randomness generation. And at first it was thought, can you go further? And some people looked at that and thought that you couldn't. They thought you can't pass the qubit on from Bob 2 to Bob 3. There's no useful Bell non-locality left. But then it turned out they'd made some implicit assumptions that didn't have to be made about measurement strengths. And last year, it was shown a very surprising result. No matter how many Bobs there are in this chain, Bob 1, Bob 2, all the way to Bob 100, for example, they can all violate independently CHSH Bell inequality with Alice 1. So we can have this chain, we just choose some number n. Each of the Bobs is violating a Bell inequality with Alice 1. They all get a value bigger than 2. Mind you, not horribly practical. The amount by which it's bigger than 2 gets appears to get exponentially small, although it's not known if one can do better. Anyway, that was by Brown and Colbeck. So yeah, one-sided recycling, very, very possible all the way. So that raises an obvious question, of course. Can you also do it the other way at the same time? And when we got into this, so let me just put this here. What about two-sided recycling? That's the title of this slide, with independent observers. So Alice 1 and Bob 1 can violate it. They pass on their qubits, one each way. Can Alice 2 and Bob 2 do it? Surely if one-sided recycling is possible all the way, this isn't much harder than that. But, and that's what we thought. We thought when we started looking at this, Xiuming raised this issue about November last year, yeah, we'll just find out how to do it. We'll know the answer. It turned out to be a very hard problem. And we've ended up with a conjecture, which we can prove in quotation marks numerically pretty well, confidently, but analytically, we only have some partial results. So the conjecture is, if Alice 1 and Bob 1 do violate it, Alice 2 and Bob 2 cannot. And the other way around, if Alice 2 and Bob 2 can violate it with their recycled qubits, that means that Alice 1 and Bob 1 never saw any Bell non-locality. They didn't. So we wanted to come up with a name for that phenomenon. One possible name is one-sided recycling, because you can only recycle all the way along. Maybe that's a good name. But we chose one-sided monogamy. The idea being it's certainly possible for Alice to be in a Bell relationship, let's say, with as many men as she likes. And it's possible for Bob 1 to be in that sort of relationship with as many women as he likes. But you can't have, say, 2 men and two women in that sort of relationship. So that's a sort of a monogamy, one-sided, how we decided to call it. Okay, so this conjecture we have some evidence for, and that takes a little time to go through, so we'll be on this slide for a little while. Please bear with me. I hope I don't trip myself up. So let's look at the graph first, and let's ignore the red curve. I'll come back to that in a later, the red line. We'll come back to that in a later slide. We're interested in this grey region. We're interested in this 2-part blue curve. Okay, what do they tell us? On this axis, how is this generated? It's saying, well, let's look at all the possible measurements that Alice 1 and Bob 1 can make on their qubits, on the 2 qubits after it comes from the source. For all of those measurements, for each different one, they'll get, if they make those measurements, they'll come up with a value of the CHSH parameter. They'll add and subtract those averages and get a number. And hopefully it's bigger than 2, so they can use it for something interesting. And here we've plotted an absolute value, but that's just for technical purposes. It has no effect. So the value they'll get is plotted on this axis, and it runs, of course, because they're sharing qubits, from 0 up to 2 root 2. That's the maximum value. And they can do something useful if that value falls somewhere in this part of the graph, because they get a value bigger than 2. On this axis, what one would perhaps plot normally is we'd search over all possible measurements made by them, Alice 1 and Bob 1, that will change the qubit states that is passed on to Alice 2 and Bob 2. They then make measurements, say W and W dash for Alice 2, Z and Z dash for W2, and you could plot all the CHS parameters for that case. And you'd be doing an awful lot of searching to plot all the possible points you can get. You'd be plotting over all measurements made by Alice 1 and Bob 1. That's a 16 parameter set. And you'd be plotting over all measurements that Alice 2 and Bob 2 could then make. That's another 16 parameter set. That's 32 parameters, plus you've got to search over all states. That's a big job. So, but luckily you can simplify that, and a lot of people have heard of the Horodecki parameter. Once you know the state that Alice 2 and Bob 2 end up with, after they've been measured, the qubits have been measured by Alice 1 and Bob 1, you can immediately work out, just from knowing the state, whether or not Alice 2 and Bob 2 can violate the CHS inequality. You have to calculate this number S star, A2, B2, that's called the Horodecki parameter. And if it's greater than 2, well, that parameter is greater than 2 if and only if there are measurements that Alice 2 and Bob 2 can make violated. So it's a good proxy quantity. It saves us searching over that extra 16 parameters. We do make an assumption, which I'll be talking more about later. In the numerical search, we assume that Alice 1 and Bob 1 make the best possible measurements of their observables that they can. They're called square root measurements. So they search over all possible observables that can be measured. You can measure observables in different ways. We assume they, in a sense, optimize the measurement they make to give Alice 2 and Bob 2 the best chance of violating Bell inequality. And the argument's not quite rigorous, but we think it's true. And these are what have been considered by everyone else in the field. So, but there is an assumption built in there. Okay, so now we know what this graph is plotting. It's plotting what Alice 1 and Bob 1 get at any point here. Say this one tells us that for a certain choice of observables, Alice 1 and Bob 1 got their parameter here, whereas Alice 2 and Bob 2 afterwards, if they make their measurements, then the Horodecki parameter has this value. So in this case, both values are less than 2. Neither of them are seeing Bell non-locality with those choice of measurements. They both have to get into this grey square here to see that non-locality. As I mentioned, we not only search over Alice 1 and Bob 1's measurements, we have to search over all the states they might be sharing to test our conjecture. And fortunately, you can show analytically, you only need to test pure 2-qubit states up to local unitaries, which means you only have to test a 1-parameter set of states. So to do this search, which is largely done by Travis Baker, after we did a more scattergun simple search, we only have to search over a space of 17 free parameters, 16 for Alice 1 and Bob 1's measurements, 1 parameter for the state. And that's done using what's called a constrained differential evolution solver numerically, which is a sophisticated thing that I don't fully understand, but it's explained in an appendix in the supplemental material of this ePrint. Okay. And what are the results? The results show that you get an envelope. You get an upper bound for what's possible. No matter what observables Alice 1 and Bob 1 measure, the parameters, these parameters can't go above this value. They can't go above this line. They can't get outside it. They can only be below. And that tells us in particular, everything's less than 2√2 here. They can get as high as 2√2. Here, they're restricted rather more severely. They can't get into the grey square. So numerically, the results very strongly support, as we're confident in those results, one-sided monogamy. No points, in other words, are in there. The red line we'll get to, that's one of our analytic results. Right, yeah, the annoying thing about an online conference, of course, is that I can't answer questions on the way because I don't know what people are thinking. Right, can we prove the conjecture? How are we going for time? Yep, time's good. No, we can't prove it completely. We can do it for several large subsets, say, including some 14 parameter subsets of those 17 free parameters. That's not bad. It's still a set of measure 0. It's certainly not perfect. But the way it's done is perhaps of some interest in itself for a couple of reasons. And also the methods may be useful in scenarios where instead of sharing Bell non-locality via qubits, you might be sharing it via some other quantum systems. You may be using a different Bell inequality. You may be only interested in sharing entanglement, not Bell non-locality, or you might be interested in sharing steering correlations. So we think the techniques might also be of some interest. So to prove it, where does the proof come from? The proofs that we do have, the partial proofs, it's this intuition. Alice 1 and Bob 1, if they make measurements and they want to violate the CHSH inequality, they have to make non-trivial measurements. The measurements have to be strong enough, if you like, projective enough, that they get something they can see the Bell non-locality that's in the state that's there, if they are sharing a Bell non-local state. So the measurements have to be sufficiently strong to do that. On the other hand, because Alice 2 and Bob 2 would also like to see CH/SH or Bell non-locality, Alice 1 and Bob 1 can't disturb the state too much, otherwise they'll destroy the Bell non-locality. If they make projective, rank 1 projective measurements, all entanglement's gone. No hope, nada. Alice 2 and Bob 2 are in the lurch. So the measurements made by Alice 1 and Bob 1 have to be sufficiently weak, not disturb things too much. In some sense, they're partially reversible, so that there's something left over, a resource for Alice 2 and Bob 2. And the way the proofs work is that there's a nice way to quantify how strong measurements are, general qubit measurements, and there's a nice way to quantify how reversible they can be if you measure a given observable. And there's a trade-off relation between the strength and the non-disturbance, or the strength and the reversibility. And so I'll talk a little bit about that. I'm certainly not going to give any proofs. I just want to talk about one of the techniques used in arriving at those proofs. Right. Let me have a drink. So let's talk about general qubit observables, or not quite general, because for the CH/SH inequality, they only have two values, outcomes, plus or minus 1. So let's talk about those two valued observables. In quantum mechanics, the most general way to describe it is via the POVM, positive operator valued measure, and we'll call that X plus and X minus. So this is one of Alice's possible measurements, say. And if she was measuring on a 1 qubit state row, these are the outcome probabilities. And the only restrictions on these elements for students not familiar with them is that the operators are positive to make sure you get positive probabilities. And these two operators sum to the unit operator to make sure the probabilities sum to 1. That's the only constraint. Turns out it's handy to represent the observable X by an operator X, which I just use the same notation because it's not really very confusing, for the following reason. You define X to be the difference of these two probability operators. And it turns out the average of the observable for state rho then is given by a similar formula. It's just rho plus P plus minus P minus. So, and so the observable and the operator have, the average of the observable is just the average of the operator. So that's why I'm using the same notation. Okay, so X tells us everything. If I know X, then I can recover X plus and X minus because I know their difference and I know their sum is the identity operator. So it tells me everything about the observable, all its statistics. So we take that operator and we just split it up into two, using the Pauli, the standard Pauli operator basis. So sigma is just the vector of Pauli operators, there's 3 of them. And when you can expand an arbitrary qubit operator that way, you'll have a constant term, which in this case we call the bias of the observable. You have a direction, which is just a unit direction, which we call the direction, the measurement direction for the observable. And there's another parameter we call the strength or the sharpness of the observable. Okay, so this is just mathematics. We can do that, and we can always take S to be strictly non-negative by choosing the direction of X appropriately. So we do that. That's how we parameterize our observable for a qubit. And a couple of special cases are interesting. If you make a projective measurement of spin in some direction, X, then that corresponds to a full strength measurement. So if you take S equals 1, you can show for these operators to be positive that B has to be 0. They have to be unbiased. So you plug in B equals 0, S equals 1, you're left with X equals sigma dot X. That's your standard projective observable. What if you take a 0 strength measurement instead? That's a trivial observable. You just find that this operator is a constant. And when you plug that into your formula for P plus and P minus, you find that the probabilities are just constant, which means you don't have to measure your system at all. If you're trying to measure a trivial observable, you just flip a two-sided coin with bias B, a biased coin. That's why B is called a bias. Okay. More generally, B and S are somewhere in between those cases. Right. Now, we have B and S, the bias and the strength. We need also to consider what happens when you measure that observable. How disturbing is that measurement going to be, or how disturbing can it be? And what's the least disturbing it can be? We want it to be not too disturbing to give Alice 2 and Bob 2 a chance when they get those qubits. So we're interested in something called the maximal reversibility, which we found quite useful. So how does it go? You can measure an observable in many different ways. You know, you measure polarizations with polarizers or of different sorts, for example, and beam splitters and so on. And depending on how you measure them, it's going to disturb the state. A lot of detectors, you measure your system and you've destroyed it. If it's a photon, you normally bung it into a photon detector and it's gone. So that's massively disturbing. We hope that Alice and Bob can do better than that. But after you've made the measurement, you're left with that part of your Hilbert space is described by a density operator rho prime. So it turns out the measurement, the particular measurement they can make that's maximally reversible up to a unitary transformation is this thing I mentioned before, a square root measurement of the observable. How is it defined? You take this POVM corresponding to the observable, you take the square root of the first element on each side of rho and add it to the square root of the minus x minus on each side of rho. And they're lovely measurements for a lot of reasons. They've been shown to have good properties. And what Brown and Kolbeck also showed in their paper, not only can Alice share Bell non-locality with an arbitrary number of Bobs, but the measurement they should pick is a square root measurement because they're maximally reversible. Any other measurement you can make of this observable will correspond to, depending on the results you get, if you get a plus result, applying a channel to the state, a completely positive map. And in general, you're going to lose information when you do that, unless it's unitary. Or if you get result minus, you apply a different completely positive map. Okay, that's talked about in our reprints a bit more as well as in this paper. So they're the good measurements to use. What does that look like if you do a square root measurement? We can have a look in the sigma.x basis what our post-measurement state looks like, what rho prime looks like. So if in that basis we started off with rho plus plus, rho minus minus as our diagonal elements, and rho plus minus and rho minus plus, we find that after the square root measurement, the diagonal elements are unchanged, but the off-diagonal elements are going to be decohered by some factor, R. And if R is 1, then fantastic. You've got rho prime as your original state. You haven't lost anything if you make the measurements fully reversible. If R is 1, that's its maximum possible value, it turns out. So R is a good measurement of reversibility. And because we know from this result of Brown and Kolbeck that square root measurements are the maximally reversible measurement, then this number R we call the maximum reversibility of a measurement of X. You may make a worse measurement, but if you make the best possible measurement, this number R quantifies how reversible it is. Okay, so we can come to this trade-off relation I mentioned earlier now. If you know the strength and bias of the measurement, you can work out the maximum reversibility. It's just this particular function. If you plug in a unit strength measurement, projective measurement of spin in some direction, you find out that they're totally irreversible. Put in S equals 1, so you've got full strength. Remember that implies B is 0. You work it out, you get a maximum reversibility is 0. You lose all off-diagonal information. You're done for. You've lost all Bell non-locality. You've lost all entanglement. Okay. Trivial measurements, on the other hand, where S equals 0, they can be perfectly reversible. If you plug in S equals 0 here, you find that your reversibility is 1. Because if you make a trivial measurement, you don't get any information out of the state. So if you like this, it's telling us a trade-off between information and disturbance. We call it a trade-off between information and reversibility, the other way around, because it works out mathematically more pretty. And here it is. Turns out in general, R squared plus S squared can never be bigger than 1. So the more reversible your measurement, and so the more likely, say Bob 2 can use your qubit, the less strong it is, which means you've made a low strength measurement, the less likely you're able to make much use of your measurement result to establish Bell non-locality. And if you make an unbiased measurement, in a sense, that's optimal for a given strength because you have equality here. If B equals 0, you make an unbiased measurement, then R squared plus S squared equals 1. And so that tells you R equals 1 minus S squared. That's as big a reversibility as you can hope for. So in some sense, unbiased measurements are very good. Okay. And it's this relation here, this natural trade-off, which lets you prove some one-sided monogamy relations. You can do some other things with it too, but I'm not going to talk about that here. In fact, I'm going to hurry up a bit. So it lets us prove our conjecture in some cases. And I might just talk about the first case. I had a couple here. So we want to use this relation. And it turns out we can prove for those quantities that we plotted here on this axis that their sum can't be bigger than 4. So in particular, they can't both be bigger than 2. But when can we do this proof? Not in all cases. We assume that observables are unbiased, and we know that's sort of optimal because this is saturated, but it's still an assumption. Maybe you can do better with biased observables. And we have to make another assumption, and we can make a choice from 2. One of those assumptions we can make is Alice's strengths that she uses for her 2 measurements are equal. Or we could make the assumption that, and we make the assumption on Bob 1's side, his strengths of his observables are equal. So if we make this assumption and they make unbiased measurements, we can prove this result. We can prove our conjecture for that case. And that's what this red line is showing. And it's showing certainly if Alice 1 and, yeah, okay. And you can see that it's above the curve here, but more importantly, it says under those assumptions, you can't get into the grey region. You're down here. You can even get a stronger relationship if instead of assuming equal strengths, you allow the strengths to be arbitrary, but you assume that Alice 1 and Bob 1 choose their measurement directions to be orthogonal on each side. And for those of you familiar with the CHS-H inequality, that's often the optimal thing to do, choose orthogonal measurement directions. Here, if you do it, they haven't got much hope in general of violating inequality. All righty. So I think I'll skip the other example and I'll put the conclusions up. There's 5 minutes or so to go, I can see. I'll quickly read through them. So first, we have strong numerical support for this conjecture. And for me, that's an interesting example where you investigate something numerically and it can lead you somewhere. A lot of my work has been done. You think about some ideas and you do some get some analytic results, and you publish, and maybe an experiment gets done. Here, numerical experiments, it's happened to me once before. From the numerical experiment, we got an analytic result. So that was good. In this case, we only get partial analytic results, these one-sided monogamy relations, and it's based on this trade-off relation between maximum reversibility and strength of qubit measurements. We hope that the analytical tools might be useful in other scenarios, such as trying to share EPR steering or entanglement. And there's a lot of work around the world on these scenarios, including in India. Some of the people have been working on in recent times. And one other thing I wanted to mention is, suppose you have a given state. Then, as I mentioned, you can calculate the Horodecki parameter for that state to see, can I violate the CHS-H inequality? But that's only if you make full strength measurements. if for some reason you only have a fixed set of measurement strengths because you have noisy detectors, for example, or for some other reason, you can ask, can I generalize the Horodecky parameter for fixed strengths in a given state? And it turns out you can. All right, so thank you very much for listening, and I think that still leaves you maybe 5 minutes or so for questions.
Yeah, so thank you very much, Professor Hall, for a fantastic, very clear talk. And you actually explained the nitty-gritties behind your very interesting results that you have shown in this paper. So I have a couple of quick questions, but in the meanwhile, let me see if there are questions from some others, from some participants. I can't see anything in the chat box. So maybe the organizers can look for among the participants. In the meanwhile, let me just make a couple of comments, very brief comments. First is to do with this two-parameter generalization of the measurements in terms of bias and strength that you have done. So you showed a case where you showed that if bias is 0, then you have strict monogamy. But if bias is 0, you can actually show more. In fact, what follows from the original work of Jisa et al. 2015 PRL paper, if bias is 0, then you have strict one-sided bigamy, not more than that. So you needn't require even go towards two-sided or one-sided monogamy. So even if you take on one Alice picks one Alice and have an increasing number of bobs, you cannot go beyond 2 bobs if bias is 0. Yeah, so that result, so that result was conjectured by Jisa and all, et al. And then in a follow-up paper, we showed that analytically using one parameter POVM. So that is a very simple calculation. And my next comment.
So you were on that paper too, then. Was Pekka Home on that paper as well?
Yeah. It was a paper published in a journal Mathematics in 2000.
That's quite right. Yes, I sort of skated over. I mentioned very briefly that before the Kolbeck-Renner result, it was thought. But yes, you're quite right. With equal strength, for example. Yes.
Yeah. Anyway, so that's one thing, and secondly is to do with it's another comment. So after your paper came out, there was a work by Cabello, I think in the archive in sometime maybe a month or so after your work, where he showed that if you actually go beyond qubit systems, if you consider Q-quartz or something like that, then you could beat this one-sided monogamy. You could have there will be no monogamy in the both sides. So you could have multiple Alices as well as multiple Bobs. So
there's
do you
some
have
interesting
any comments on that work? Yeah.
Yes, I do. So Ed Cabello wrote to us after our reprint came out, and we discussed this, and he said, I believe I can show this. And he posted his ePrint. However, that ePrint's actually got a serious error. His example doesn't work. Well, it's got beautiful diagrams with Bob Dylan for one of the Bobs and so on. But his overall point's correct. And after, we pointed that out to him and pointed out an example that does work. And that's in one of the 2 ePrints I mentioned. In fact, it's this middle point here, how you can evade the conjecture. And you're quite right. If you've got, instead of sharing 1 qubit state, you share, say, 2 qubit state, two qubit states, that'll be a Q-quart, or maybe M qubit states, you can actually get 2-sided recycling with up to M observers on each side when the observers are independent. So the problem with Cabello's ePrint is that the observers aren't independent. When you look into the example, they essentially know the results of the observers before them. But yes, you can construct it. And the way this construction works, it's in a later reprint of ours, is using the Brown-Kolbeck construction and just using it in a different way, similarly to what Cabello does. And we acknowledge Cabello in that result. Yeah, so it's an interesting case. I thought he would correct the ePrint, but he hasn't done so yet.
Okay, yeah, thanks for that amusing anecdote. And it's also interesting that we can now go beyond this monogamy for Brown and Kolbeck's construction. But just one more thing, following it up, that see, normally whatever experiments that I'm aware of that has been done in this area of sharing correlations, not only Bell non-locality, but as you mentioned, sharing other kinds of correlations like entanglement or steering, they have been done for unbiased measurement scenarios. So people have actually, a number of groups, I think 4 or 5 groups around the world have done these experiments. And
Yes.
so the question now is it at all possible realistically to do experiments in the bias scenario? In that case, say Bob n minus 1, if he chooses a certain value, a certain degree of bias, then Bob n or Bob n plus 1 should somehow be aware of that bias parameter. Because without that, how can they choose their bias parameters correctly to go beyond, to go to a large number of observers?
Yes, that's a really good question, and I don't have a I don't have a very good answer. We've done some numerical work that at least show it can be advantageous if Alice 1 and Bob 1 make a biased measurement. What I can do is point to this last paper here on the archive, just put up a week or 2 ago, which only looks at the case of trying to just Alice 1 and Bob 1. There are no other observers. Should they make biased measurements or unbiased measurements if they have given strengths? It turns out that in many scenarios, if they share what's called a T-state, for example, it's optimal to measure unbiased observables. They'll get a bigger violation of the inequality if they measure biased. They have to measure biased observables, which was a bit of a surprise to us initially. And we don't fully understand the physics. And I think another part of the question you raise is perhaps, as you say, all the prior literature typically considers making unbiased measurements. So you have to consider how to measure successfully a biased measurement. The part of your question is whether subsequent observers need to know about that bias. Yeah, I'm not, that's something I haven't looked at in any detail, so I can't comment on. But yeah, very good question.
Yeah, thank you anyway. So are there any other questions? Because I don't see any hands raised, or I'm looking at the participants, because also this is a new platform for me, so I don't know. Normally,
yes, it's new for me. It's not easy to use.
Yeah, or Microsoft Teams, one can see raised hands, but here I don't see any. So unless there are
one quick question.
Yeah, sure, please go ahead.
Okay. Suppose if someone wants to experimentally verify this method, what all the care one has to take in terms of recycling the qubit?
Sorry, what is the what it takes for the recycling?
The qubit recycling, whatever you suggested, you proposed.
Yes.
What kind of utmost care one has to do when someone wants to perform this as an experiment?
Experimentally, what do you have to consider? You have to have fairly clean, reproducible measurements, I guess, is the main thing, because the amount of Bell violation you get becomes quite small after even sharing to 2 observers. There's an experiment we suggested, for example, where instead of Alice 1 and Bob 1 choosing their measurements with 50-50 probabilities, they choose with some other probability. For example, if Alice chooses a very weak measurement most of the time, and a protective measurement just has to be, turns out, less than 8% of the time, then she won't disturb her state very much at all. And it turns out that you can have 2-sided qubit recycling if Alice 1 and Bob 1 both do that. But the amount of Bell non-locality they see is about 2.1, which will give you a very low rate. So I think that's possible to see experimentally. It's just a matter of adding noise to projective measurements to see it. But the amount of useful Bell non-locality is rather small and would get worse. So I have to wonder whether this is something more, foundational interest, sure, but experimentally, interesting to do a proof of principle, but I'm not sure it's going to be useful beyond that. I don't think it'll be too difficult to do that experiment, though, similarly to experiments that have been done for one-sided recycling. So thank you for that question.
Yeah, thank you.
Yeah, so thank you. So if there are no more questions, then let us thank Professor Hall once again. And it's late in the evening for him. So I hope
yes.
you will
Sir,
enjoy your dinner if you have already hadn't had it
Yes.
by now. And yeah, so we look forward to seeing you sometimes here, not only virtually, but physically when the situation improves, so that we can carry forward our discussion. And thank you very much.
That would be great. Thank you very much.
Thank you. Oh, there is one more. I can hear a voice. Okay, very quick question if there is one. Okay.
Yeah, there is a question. What
Yeah,
are
please,
the trivial measurements?
Sorry, what was the question?
The question is, what are the trivial measurements?
The qubit measurements. Oh, what measurements do you have to make? They're if you like, a type of weak measurement. You instead of which you can make, for example, by inserting a small optical plate. If you do polarization measurements, which weakly gives you a polarization effect on your qubits. Yeah, I can't really give you the reference. There's a standard way of doing it, which I think Andrew Dressel and Jordan, Andrew Dressel and Justin Dressel and Andrew Jordan use. But yeah, there are ways of doing these. They're a type of weak measurement you can make, but I can't give you any more details off the top of my head. I'm sorry.
Okay, so I think we are completely out of time now. So once again, thank you very much.
Thank you.
And we now move on to the next presentation. Is the next speaker round? Okay, thank you very much. So yeah, so Professor Hall, if you could, yeah, you have already unshared your presentation, I think. So the next speaker is Professor Christophe Coutu, and he's from the University of Technology of Troyes. And he actually did his PhD in physics from University of Paris-Saclay in 2006. And he works on quantum optics and quantum dots. And he spent his postdoctoral tenure at Waterloo in Canada, where he worked on quantum cryptography and foundations of quantum mechanics. And since 2009, he has been an associate professor at the University of Troyes. And he's currently director of the Laboratory Light Nanomaterials and Nanotechnologies at UTT, CNRS. So he's going to talk, the title of his talk is a new platform for quantum photonics applications. And once again, very good evening to you, Professor Coutu, and welcome. Please, you can please start your talk. Thank you.
Thank you. Thank you very much. So I guess you can hear me. You can see me, but you can see my screen. More to the point, if I do this.
Yeah, sure. So we can hear you as well as we can see your screen.
Okay, and how's the screen sharing? Is it full screen, or because I have two screens, so sometimes I have to switch? Is that okay, or?
Yeah, now it is not quite full screen, but we have a split screen from you. Right. So we are seeing two different pictures. Now it is full screen. Yes, it is full screen.
Now it is. Okay, good. Then this is good. Oops. All right, very good. Thank you. Thank you very much for the introduction, and thank you very much for the invitation. So yeah, so I slightly changed the title, but the idea is the same. So you know, I called Towards Quantum Technologies Using Nanophotonics. So introduction has been made already. Thank you very much. So indeed, I'm an experimental physicist, and so today I will talk about some of the experiments that I'm pursuing and trying to go forwards into some of the quantum technology applications. So it will be very much sort of dirty work, experimental work, but that's the way it is. You know, you have to do that at some point for sure. And so I wasn't quite sure, not quite sure what kind of audience I have. So I decided to go from you know, general context down to what I'm doing. and hopefully there are some things that you already know, then this is good, and some others that you will discover. So I work at the in a place called Troyes. So my name is Christophe Couteau, associate professor at the one of the 3 French University of Technology. So before, just briefly to show you where it is. So I don't know if you can see my mouse, but because already French people don't always know where Troyes is, but if you have Paris, so this is France, Luxembourg, and this is Belgium, then Troyes is about 2 hours southeast of Paris. So it's a city with a lot of history, sort of timbered houses. It's also so it's a very nice place. You're all welcome to visit, please. I know Shubhashis has done it already. But it's the birthplace of the Templars Knights, for those who like Dan Brown and etc. There's also a major selling point is that it's in the Champagne region. So I highly recommend if you like Champagne. And for the introduction, I should say that there's recently we are embarking into developing with 7 other universities in Europe the first European University of Technology, and we are quite excited by that. So this is what the campus looks like, and in particular, so my laboratory. So indeed, I'm the director of the L2N, which is the laboratory for light nanomaterials and nanotechnologies. That's been 2 years ago now. It's been for 2 years. And we have about, well, you can see, so some office space, but also some lab space, about 1,000 and a bit more square meters of lab space, and about 3/4 of them are in clean room, which is necessary for doing nanotechnologies and nanoscience, as you will see. And again, just to introduce you briefly what we do at the lab before I go into what I'm particularly interested in as a researcher. My laboratory research signature is observe, study, and control the light at the nanoscale. And for that, we have three different ways of doing it, which is standard in a way, so numerical modeling and simulation. We also have instrumentation and fabrication of nano objects, and also material growth of nano objects. So of course, obviously, I won't be able to go into details of all of that, but you will see some examples that can be used for quantum technologies. And to finish on that, so my laboratory is mostly around nanotechnologies with some application in quantum technologies, but not just. And what we like to say is that, in fact, we've always been doing nano technologies in the region, in particular in the city of Troyes, because you can see here some beautiful medieval stained glass, and those are due to plasmonics and due to light interaction with metallic nanoparticles. And so, in fact, we've been doing nanotechnologies in this region for centuries, but without necessarily knowing it. So that was a quick sort of introduction to my laboratory and what we do in general, and to also give you an overview of the University of Technology of Troyes, where not everyone is aware. But for today, so indeed, I want to focus on what I particularly am interested in as a researcher. So here's the program for today. So first, I will start with a very general context of quantum technologies, assuming that most of you know it, but again, it's always good to see some things we know maybe with a different angle. Then I will focus on to, what is my qubit? So what is the game? So what is your qubit as an experimental physicist? So mine in particular is the photon as a qubit, and the diamond platform as a full integrated platform. I will talk about this. And then I will say how, in sort of concrete terms, how what we call nanophotonics could be a way to develop sort of complex experimental architecture for perhaps, let's start with sort of toy models, and then maybe later on quantum simulators and maybe more. And for that, I will mention the photonics platform that we use. I will describe the nano emitters that we use, mostly color centers in diamond, not just. And I will also explain how an efficient light matter interface is very important, and how you need to actually devise components that you can efficient components that you can use for scaling up, for instance. And then I will conclude onto what I talked about and give some perspectives of what's next in terms of sort of next levels of work regarding this platform that we want to develop here. So the context of quantum technologies. So again, this is probably something that most of you know, but this is good to review that in terms of practical applications. So there are two limitations as the sort of classical technology as we know it as of today. The first one is a very physical limitation, is the so-called end of Moore's law. So Gordon Moore, who was the CEO of Intel, predicted in the 60s that the number of transistors on an integrated circuit would double every 2 years or so. And that was pretty much true. You can see here as a function of the years, the size, typical size of the transistors or the features of the transistors. And you can see from 3 microns in the 80s down to a few nanometers at the moment that indeed this trend is sort of satisfied. But there is nowadays a slowdown. And the reason is because, well, when you start to be at too small sizes, like few nanometers, then the classical picture where, say, an electron that is not supposed to go through an oxide layer, then is sort of bounced off or doesn't go through an oxide layer, or insulating layer, then this version is not true anymore, because the quantum picture tells you that quantum tunneling can occur. And in concrete word, what does it mean? Is that, well, basically now you have a transistor that basically can trigger a signal where it is not supposed to, because the electron or the electron signal was not supposed to go through this insulating barrier, and yet it did, thanks to quantum tunneling. So that's the first limitation, where size matters, and there's an end to that integration. The second limitation, which is probably even more limiting, is the fact that there are currently some problems, like, again, very down-to-earth problems, like combinatorial problems, optimization problems in mathematics and computing, that are unsolvable. Unsolvable in the sense that they are unsolvable in a reasonable time. Okay, so the traveling salesman problem, for instance, is an example of what we call an NP-hard problem. And there are more, and they are even more complex ones. So that means those are problems that are very difficult to answer with classical computers. And there are others. I'll just give you 2 examples. So the second example is, well, we know, is that in quantum mechanics, when we want to know, what an atom or what a molecule actually is, then we need to solve the Schrödinger equations. We need to solve the so for a given Hamiltonian, and we need to find the energy levels of that atom. So for hydrogen, okay, for helium, okay, but then as soon as we have more complex molecules, then unless we do some hypotheses and assumptions, then it's impossible currently to exactly solve energy level issues of some complex molecules that we can in a way that we can for the hydrogen atom, for instance. Okay? And so these are just some examples, but there are some more. And perhaps what is even worse, like I said, is that for some problems, we know that no matter what, computers now are not able to deal with them. And in fact, the classical computers now will never be able to deal with these problems, no matter how big they will be, again, in a reasonable time. And that's where the idea in the beginning kicked in to say, well, how about we actually use that seems to be the problem in the first place for some issues, the quantum physics, in order to solve our problems, or some of our problems. And so that launched the start of the interest of first quantum information, and then quantum technologies. So there are some algorithm like Shor's algorithm, Grover's algorithm, and then some other algorithms where clearly indeed the use of quantum physics makes sense to solve some complicated issues otherwise for a classical computer. And nowadays, in the last few years or so, then the real question is more an engineering issue, a technological issue, is how do we actually implement, in the lab, those potentially complex algorithms. And that's where quantum technologies and that's where experimental physicists have a lot of work, and also quantum engineers. And so I gave you here some examples of the technologies that exist right now. So there are many of them. I'll just give you 3 examples. So there are people working on superconducting circuits and using superconducting qubits as the main workhorse for their simulators. So that's the case with IBM, for instance, company IBM. There are other people working with trapped ions or trapped neutral atom, where you would trap single atoms or single ions in this case, so-called pole trap, and you will make sure you can control optically the interaction between these atoms in order to basically have complex single or complex 2 qubit gates, and have entanglement and entanglement swapping, etc. Other people, so that would be, there are examples, a startup company in the US, but they're working, people working in various places around the world. Here's an example of ETH, for instance. Another platform is, which was one of the original platform predicted theoretically, is to use silicon, which seems to be a very good idea because silicon is already what we use for standard classical computation and information, and to control a single defect, a single atom. In this case, it could be a phosphorus atom within a silicon matrix. And the idea is that this phosphorus atom would basically behave like a 2-level system, like an electron spin that you could control when you see these various electrodes around it, to form, say, a single qubit gate, for instance. And then, of course, the idea would be then to place another one next to it, and then another one, and to basically have interaction between many of these sort of isolated single electron spin. So there are other platforms, but what's of interest for me, specifically for us, is to make use of photons in condensed matter. And there are, as you will see later, there are 2 major reasons for that. The first one, as I will describe later, is because condensed matter can provide potentially all the ingredients that one needs for a quantum computer. And second of all, you need to couple that to photons, because at the end of the day, this is what currently is doing. I mean, the reason why you can see me right now is because there are some photons traveling into optical fibers between France and India. And at the end of the day, this is how communication is done. And this is how these future quantum simulators, quantum computers will have to talk, is using photons. So you have, at least on long distances. So you have a particular interest, or at least we have a particular interest into these specific platforms. So, well, this is a slide that is probably not necessary, but in all of these platforms, so as usual, you need to find your qubits. So you need to be able to define your qubit. So in superconducting qubit, it would be, for instance, a charge qubit or a flux, magnetic flux qubit. In trapped ions, it could be the collective, either the 2-level system of the ions, or also the collective ensemble. For the phosphorus atom, as I said, it would be the equivalent of the electron spin of the phosphorus atom, and so on and so forth. So at the end of the day, you want a system where you can have standard qubit behavior where you have a superposition of two states 0 and 1. Now, what the 0 and 1 is for your physical system, that's a different story, but you need to be able to tune this qubit at will with some coefficients alpha and beta. So for us, what's interesting is to use the photon as a qubit. So what's the starting point? So a quick reminder, electromagnetism. So electromagnetism is driven by Maxwell's equations, right? Light is an electromagnetic wave. So I picked that up from Wikipedia. It's the oscillation, electric field, magnetic field. Okay, no problem. It's electromagnetic wave. So we can define a so-called propagation equation where we can exactly tell what the electromagnetic wave behavior will be. Okay, so we can also, to some approximation, approximate this electromagnetic wave to a plane wave. Okay, this is all very well, no problem. If you do this, then again, in classical optics, then you can define polarization state of the light. In optics, polarization state of the light is the vibration of the electric field axis. So if you have, say, a wave that propagates towards you towards the z-axis, then you can define the x and y axis. So the x-axis, so the electric field as it propagates, oscillates along the x-axis, then you have linear polarization along x. You can also have a linear polarization along y, again going towards you. And you can have any linear polarization, like the linear polarization at 45-degree angle, so plus 45 and minus 45 degrees, so that would be diagonal, anti-diagonal. And you can also have a bit more complex polarization of your light, which is a circular polarization, so either right-handed or left-handed, going towards you. Okay. And so this is standard optical waves. You know, we can, like I said, you can use plane waves to explain that, no problem. But the good thing is that if you now go to the quantum optics realm, which I'm not going to do, but if you quantize Maxwell's equation, then you can define the quanta of light, the quantum of light, so the photon. And the good thing is that, which is now a quantum object, a single quantum object. And the good thing is that all these properties of polarization remains valid for the photon. So in other words, that means that you can define a qubit now as the polarization state of your photon. So in this case, you could decide to say, okay, well, the polarization, linear polarization along x for propagating along z, then I will call this my state 0, and polarization along y, I will call it my state 1. And then it's very simple. If you go to 45-degree polarization, you already have a superposition of state, because it's simply, well, with the factor of the plane wave, simply ex plus ey, which gives you the diagonal axis. So you have the plus minus 0 and 1 qubit state. And then the more general one would be circular polarization, where the only difference between the linear and the circular is that you have a dephasing on along one of the directions. So in this case, you can see that there's a dephasing of pi over 2 along the y axis. And that in sort of qubit notation, in the Bloch sphere, is equivalent to having I complex imaginary part in the qubit now, in your right and left-handed circular polarization qubit. So here we go. So you have everything that is required now. And like I said, the good thing is that you can manipulate light with standard optical elements. And as photons will follow, so polarization state of photons will follow the same rules, then that means practically in the lab we can buy elements. So for instance, you can buy a so-called half-wave plate, which will rotate a linear polarization, so say from vertical to 45 degrees, for instance. You can use a so-called quarter wave plate, where in this case you can go from vertical to circular, so you could go from such a state to such a state. You can also have splitters, so something that can split your polarization state. So if you come with photons along H and V, you can split them. So say the vertical photons, so your one state qubit on the left and your 0 state qubit straight forward with the horizontal polarization, and so on and so forth. So the good thing is that all the classical optics elements that we have, we can use them to control single photons in the same way. Okay, so that's one thing. So at least for propagation, the propagation of the state of your signal, of your information, photons is very well adapted for that. Now, as I said earlier, this is not enough. You can, so there are companies, there's a particular, and there are people working on this where they only use photonic platforms, so they only use photons, single photons and tangled photons as qubits. So this is very well, but if you go back to what an actual classical computer is, then you realize that there are at least 3 elements that you need. So this is the sort of so-called von Neumann computer architecture. In a computer architecture, there are inputs, outputs. There is a central processing unit where you've got the control unit, the arithmetic and logic unit, and then you have a memory unit. Okay, so basically you need ins and outs. You need to be able to computation to process signals, and you need to the memory at some point to be able to store in and store out some information. So in fact, even though a quantum computer does not exist at the moment, but a quantum computer will require the same thing. So it will require input output, which could be photons, for instance. So that would be traveling so-called flying qubits. You will need a platform at a given place where you can do the computation. So that could be what I call stationary qubits, where you have a single qubit gate or 2 qubit gates in order to build any kind of quantum computation afterwards. And you need a memory unit, something where you will be able to store information, albeit this time quantum information, so much more complicated, but something to be able to store. And if you look into that, there aren't that many platforms that can potentially do that. And one of them that seems to be very interesting is the so-called diamond platform. And that comes from, so the first, actually the first article that was that foreseen that was the article, this famous article by Jeff Kimball. So that was in 2008. And in this article, Kimball exactly proposed what I said. He proposed to have a quantum internet. It was actually, the name of the paper was A Dream of a Quantum Internet. And he exactly proposed that. He said, well, you know, computer is something that will have quantum nodes, and these quantum nodes, so there will be quantum channels in between these nodes. So these quantum nodes will be basically interaction boxes where you will have light matter interactions. So that's where the processing would be, and the photons traveling. So there would be the quantum channel between one node to the other. So you could have entanglement between 2 nodes. You would also need at some point memories, be able to store in, store out some information. And in this case, in the case of Jeff Kimball, what he had in mind was single atoms and cavities. Like I said, there are some other platforms for conducting trapped ions, which would be very similar to this kind of platform. But at the end of the day, all of those seem to be or may have potentially some limitations in scaling. So as I said, ideally, as usual, you want to look for condensed matter platforms. And they are now, the choices is getting less. And in particular, the one that's of interest for us is the so-called diamond platform. So the diamond platform is interesting because, so here you have three examples of work that has been done in diamond platform, where you have these three ingredients I was talking about. So the first ingredient is to be able to compute or to control gates on a stationary level. So have somewhere fixed where you can control your computation. You should be able to have a memory somehow, and you should be able to transfer information from one node to the other, so from one place to the other. So in Diamond has this particular capability. And the reason is because in Diamond, as I'll get back to that later, Diamond has what we call color centers, which are defects. And these defects, in fact, in this high bandgap material are atomic-like systems. Okay, so they're very much like the idea of what Kimball had in mind. Of course, not as clean. Single atoms are always, for an experimental physicist, is always the cleanest system, at least on paper. But in practice, you want to go to these more potentially scalable system, but then problems come in. But at least in Diamond, so you here put three examples where you can see here how, so by some simple experiment, they managed to control the electron spin, a single electron spin of one of these color centers in Diamond. And they could find here the so-called T2, so the coherence time of this electron spin up to milliseconds. So that was in 2009, using some technique taken from NMR techniques in the 30s. They were able to basically control, manipulate a single electron spin. So that's very good because that's basically your single electron spin, your single gate. More recently, people have also realized that these defects, this atomic light defect, which are electronic states, can couple, so these electron spins can couple to nearby nuclear spins that are in the matrix of Diamond. The nuclear spins are very good because if you can transfer the quantum state to a nuclear spin, then nuclear spins are much more robust to decoherence. And in other words, that means that they can keep this quantum information stored in them for much longer. Okay, much longer means seconds, or perhaps even minutes or days. Okay. So that's very good. And that was the first experiment where you can show that have this capability as well. And then even more recently, what was done is the entanglement between two color centers. So in this case, SIV stands for silicon vacancy center. I'll come back to that later, but one of two defects. And what you see here is basically a beam of diamond. In this beam of diamond, they were able to irradiate two color centers in a certain distance. You can see here is about 25 micrometers. And each of these centers could emit a photon. And what they managed to do is to basically realize an entanglement between these two defect centers by what's called superradiance effect, where basically what they had is they had a single photon emission coming from one of the centers, but they cannot tell which one. So there's basically entanglement between the photons can be coming from this one, not this one, or from this one and not this one. And so they could see this sort of bunching effect of superradiance, where basically they could have an entanglement between the two centers. So between manipulation of a localized one, between be able to entangle two centers, and between having a local memory next to one color center, we can see that potentially we have everything we need. So, you know, the question is, can we really have this all diamond platform? So the answer is yes. So people are trying to do this, but it's not easy for two reasons. The first reason is because diamond is actually, first of all, is very expensive. It's also very expensive on its own, but it's also very expensive to process experimentally. And it's also not necessarily compatible with already existing photonic platforms, okay, which are usually made of glass. But that's the first thing. The second thing is that at the end of the day, as I said earlier, is that when you have, so say you could have a small quantum simulator here made of diamond and another one here. At some point, that was the idea here, is that you need to link you need to link these platforms together, and this can only be done with light. And light extraction and light connection inside, outside and inside the diamond is actually very difficult to do, and there can be lots of losses. So you can see that although this platform seems to be nice, there is still some technological engineering issues to solve. And that's why what we would like, we're interested in, is to basically try to couple the best of both. So what is the best of both world? Is the best of already was existing in photonics. So standard photonics using, so here would be a standard photonics, so it's a schematic of a glass waveguide, so made of glass. And then to make use of diamond, diamond, but in a nano shape now, and to make use of nanomaterials. And the reason for that is because these nanomaterials, so it could be diamond in a nano form, so nano diamonds. The hope is that you can get the same properties that we have here, so single electron spin manipulation, memory, entanglement between the two. Except that now, you, in an ideal world, you should be able to position your nano diamonds, your nanomaterials, so your nodes, wherever you want on your photonic platform. And this is very good because now, ideally, at least, what you would have is you have these nodes. You can manipulate these nodes, so they could be manipulated optically or also electrically, actually, also with magnetic field. So you can locally, like it was done in such experiment where you use magnetic field and optical field to manipulate your electron spin. So that can be locally done. And you would have, through the standard photonics platform, you would have the link between the two nodes. So you have what I call optical bus, which itself can be easily coupled to a network of optical fibers, for instance, that can be then launched to another photonic platform on this one, photonic waveguide, here or somewhere else. Okay. So the idea is to basically use nanophotonics in what we call integrated optics, which is basically what people do at the moment using glass substrate or silicon and insulator substrate, which is used for classical photonics at the moment. And to couple this with these diamonds in nano form, so these nano diamonds, which potentially harness all the ingredients that you need: memory, single spin manipulation, and emission, in and out emission of single photons. So for that, you need a to-do list. So you need to be able to have an efficient light-matter interaction. For that, you have what we call nano antennas. So this would be what these nano antennas would look like. I'll come back to that later. You need to be able to have n emitter interaction or few emitter interactions. So this can be done through an optical bus and through single photons. So according to my student, if you've never seen a single photon in your life, that's what they look like. You need waveguides, so with very low losses, which is also a major issue that you probably do not have necessarily with diamond platforms, that they can be very lossy. So you actually do lose photons. So glass waveguides do have this property. And you need something that is compatible with optical fibers and optical network, as we know them now, in order to be able to spread and to do, say, entanglement swapping, for instance, to various places, various spatially different places. So, so for that you need, as I said, two ingredients. So first is the photonic platform, and second is the nano emitter, the nanomaterial. So for the photonics platform, what we use is so-called, so it's a glass waveguide, and we use the so-called ion exchange technique. So this is a partnership with a company in France called Team Photonics. You have an example here of a glass waveguide, and you can see two connections here of an optical fiber. And the idea is you start from a glass substrate, a bit of glass, standard glass, and then by putting some silver salt on top of it, you will do an exchange of ions between the naturally occurring sodium ions in your glass, if you use such a glass, and the silver ions that are on the salt, the chemical salt deposited at the surface. And there will be an exchange, these ions, so this could be done by heat, you could do it by heat transfer, I mean, thanks to heat diffusion, or you can do it using an electrical field. But at the end, what you do is you replace some of the sodium atom by the silver, sodium ions by the silver ions. And what you end up with is a place where the refractive index, you can see here, is higher in this region than it is for the rest of the glass. And so you can have this at the surface, or you can bury it. And the good thing about this now is that, well, this is precisely what you have in optical fiber, is you have two different glass materials with slightly different refractive index, and the one in the middle being a higher refractive index, so that the light will be able to now propagate, be guided through that, that waveguide. So the big advantage of such a technique is that it's a very low loss kind of waveguide, so it's less than 0.1 dB per centimeter. It's a fairly good confinement, and the light is very well confined into that waveguide like you would have in standard optical fibers. It's also low cost. These techniques of ion exchange is actually very, is not very costly, so you can have very wide and large scale. You can have single mode propagation in the visible spectrum, or in fact, up to the infrared spectrum as well. So that's good if you want to have single photon emission, single photon emission through this waveguide for a given quantum state of light, then you can. And you want it to be compatible with commercial optical fibers, which is the case because you have now glass-to-glass connection, which is easy. So there is a very high interest in doing this. And on top of it, this is perhaps the only platform where you can see that if you put something on top of it, you can actually have the interaction between something on top of it, say nanomaterial, and the waveguide itself. Okay. So now I'll come back to the actual coupling of the nanomaterials on the waveguide, but now I want to go back to the color centers, nano diamonds. So I said the diamond platform, what we're interested in is color centers. So those are actually defects. You can see here what is a so-called silicon vacancy defect looks like. So what there is that you have two carbon atoms missing in the diamond lattice, and you have a silicon atom in between these two vacancies. Okay, and so this silicon vacancy, so SIV, so-called SIV, is basically like a two-level system embedded in the matrix, in the diamond matrix. Of course, because as I said, it's a condensed matter system, so it's a bit more messy. So you have so-called spin-orbit coupling. Due to the matrix, you also have effects called Jahn-Teller effect. Whatever you have interaction between this isolated defect with the matrix still. And in fact, it turns out that what you have is a bit more complex symmetry than just a two-level system, because the upper state and the lower state are actually degenerated. But the fact is, at the end of the day, you get a nice, clean atomic light system, which can emit light. As you can see here, the room temperature luminescence of such single color centers and nanodiamonds. You have here an image of many, many nanodiamonds, and they look like small pebbles put together. So you want to isolate them. And you can see here the low temperature photoluminescence. So it's done at 4 Kelvin. And you can see here the 4 emission lines, which are basically the 4 transitions called ABCD from the 4 allowed transitions from the 2 upper states to the 2 lower states. So you can see that this is a very nice system potentially because well, it's an atomic-like system. So that's for SIV. It also works for GeV. But in this case, it's in a nanodiamond form. So those nanodiamonds, so you can go further studies. You can, so if you isolate one of them, so in this case, we did some experiment and recently published some work on germanium vacancy, but actually the symmetry is exactly the same. It's just that you replace germanium by silicon. And what you can show is you have also luminescence at a different wavelength, but you can show that if you isolate a single nanodiamond and a single defect, then you have so-called anti-bunching experiment where you have a true single photon source. So 1 photon at a time, which is essential in order to work on a given single color center, which would be your stationary qubit. You can carry on to these properties. You can put that in a magnetic field up to 8 Tesla, and here you have 2 examples. So it's you have to see. So here are the four lines here at the beginning. So you can see them 1, 2, 3, 4. But now all these 4 lines, they will be split by the Zeeman effect, and you will have 16 now different transitions between all the upper states, the upper branches, to the lower branches down to from the upper state to the down state. So you have 16 different. So you can, use standard spectroscopy, the fine spectroscopy of those diamonds, and also you can find what's expected is the fact that silicon has actually 2 isotopes. So silicon 28 is a standard one, but you also have silicon 29 and silicon 30. And what you can see here is you have 1, 2, 3, 4, these 4 transitions I mentioned. But you can see some of these peaks have doubled. You can see here and you can see here, and they have 2 transitions. So in fact, what you see is the silicon 29 and silicon 30 presence of SIV centers in this case, a bigger nanodiamond. What you can see is the 4 transition lines from the silicon 28 and the 4, but slightly shifted, the 4 from the silicon 29 and the 4 from the silicon 30. So that's at 0 Tesla, and then at 9 Tesla, then you get basically a big mess because you have the 4 from the silicon 28 16 times. That's what we have here. And in this case here, well, this gets blurry because in this case you have all the 16 from this 4, also from this 4, okay, and from this 4. So you have basically a big mess. But the fact is you can have interaction, you can have nuclear spins nearby your transition now, and potentially, as I said, use these spins for quantum memories as actually, some recent work also used nuclear spins for quantum memories, but also as a qubit ancillars. Right. So I will have to finish. There's a lot more I wanted to show you, but I'll be very, very brief. I just want to focus on one more thing, is that, okay, now we have the platform and we have the nano materials, nano diamonds. So the question is, how do you put them together? Because if I take a nano diamond, like I just showed, and if I put it on one of these waveguides, then the light between the nano emitter and the waveguide, so the coupling of the light, would actually be very low. Okay, so it means that you need to have an efficient light matter interface between your nano emitter and your photonic platform. Okay, and for that, you need to have, so as I said, if you just put the nano emitter on top of it, then the coupling will be very bad. So you need to have an efficient interface to make sure that most of the light from this emitter will be coupled into the waveguide. This waveguide can be used as a bus to perhaps having another nano diamond here or there, or further in another platform. But you need this interface, and that's a big engineering issue. So this is something we've been working on. So I'll skip some of these slides. I'll focus on this one. So what my colleagues have managed to do is what I call nano assembly. So what you see here is, so the line here, in figure B, is a polymer line. Okay, so it's actually photopolymerized line of polymer, and on top of it, what you have are, in this case, polystyrene nanoparticles. And the idea is that we can nano assemble, so we can make sure that we have any structures. You can see here S shape, or you can see here even 3D structures made of polymer, or simply at the surface, and we can graft any particles, so polymer nanoparticles, also gold or silver nanoparticles, but also some others, magnetic nanoparticles in this case, but also nanodiamonds. Okay, and the good thing about this, so you can see here an image, you can see the scale bar of 200 nanometers. So here is a polymer dot. So it's a functionalized polymer dot, so that it can actually grab or attract the nanodiamond onto it. Okay? So now we have a way to precisely position a nano emitter, nanodiamond, nanomaterial. So that would be the stationary qubit onto a given place. Okay? So you can see here when you have the luminescence from many emitters, so you have here, and then from only 3, you can control. So you have 3 emitters, here you have 1 emitter, 1 nanodiamond. So here to show the luminescence difference, when you have many, you have high luminescence, few, you have low luminescence. Okay. And we can do that to a single nano emitter. So we can do that. So there was recent work we've done where we have a nanotube. We can couple a single emitter. So what you see here is a polymer. So we managed to photopolymerize only at the corner of this cube. Again, look at the scale bar. We're talking about a cube of about 70 nanometers side. And in here, we managed to only have 1 nano emitter. In this case, it was a nanocrystal or quantum dot. And we saw that we control that by a single photon emission. So we managed to have, with this environment, so very close environment, to only have 1 emitter, to graph down 1 emitter. So the next step now is to say, well, that was done on a substrate, that was done on some lines with bigger particles. We can do that, we can have nanodiamonds. So let's now put this together. We can do it with nanotubes, and let's put it together. And that's where we are at now at the moment, is to be able to now couple these nanoemitters to our photonic platform. And once we do that, the idea, as usual in experiments, the most difficult is to have it for one. But once you have it for several, then it will be, once you found a way for several, then hopefully it will be easier. Then you can have one platform and another one, another one, and another one. So that's the, so one stationary qubit, another one here, another one here, and there. Then your optical bus to be able to couple those together. So right now, The first stage is to be able to do an integrated single photon source. So I guess that's what it will look like. I don't know yet. Just took a picture of an old oscilloscope, but what we want is to basically have this. So it's a project with CNRS Innovation. You have a black box, like a box like this, where you have a USB key at the entrance and then just an optical fiber at the output, and have single photons coming out. So that would be the first step, which we are working on at the moment. Some nice results that we are about to submit. And then the next step would be to go on to do more complex networks. So here is polystyrene, but we want diamond, and to be able to do several nodes. Right, I think my time is almost done, so I will conclude. So I promised a very experimental physicist point of view on a platform, the one we're working on. So we find that sort of what we call our hybrid platform between photonics and nanomaterials, so nanodiamond, is very promising for stationary and flying qubits to be able to put them together. We are working, and we have some nice first result of the efficient use of nanophotonics, and this interface here between antenna and nanotapers and structured surface is the realm of nanophotonics, to be able to integrate sort of microscale photonics with nano objects. And it's potentially scalable and hopefully all integrated in the near future. Of course, there are many other questions that we have to answer as well. Is the fact that we need to see photon indistinguishability and coherent control of our photons, which still to be remain. Ideally, we also would like to be able to implant ions as we will in these nanodiamonds. And of course, now we will need to manipulate single and 2 qubit gates onto these nanodiamonds, electron spin of the nanodiamonds and the nuclear spins of the nanodiamonds, which also, so there are some works that have been done, but there's still a lot of work. And with this, I will stop here. So if you have any questions, please do not hesitate. And I thank you for your attention.
Yeah, so thank you very much for your very nice talk, giving us an overview of the state of the art of using nanophotonics as a platform. And then now we have just about a couple of minutes for some questions. So are there any questions? So let me see in the chat box.
Yeah, can I ask question? I am RP from PRL.
Yeah, please, RP. Yes, please go ahead. Yes.
So you showed that single photon source and waveguide, glass ion exchange waveguide, and then you have TiO2, and on top of that TiO2 you are putting your nanodiamond. So people talk of bow tie cavities, so interaction will be better. Are you trying bow tie cavities? You have only one part, this triangular thing. Could try bow tie and put nanodiamond there, so it will have better interaction.
Yeah, very good question. So yeah, so okay,
yeah,
exactly, Sandy. So this is one, actually there are different there are many schemes that can be used, but you're right that the whole point, and that's what I was trying to describe, the whole point is basically to be able to have an adiabatic change between a nano object and a micro scale object. Okay, and this, you're right, you need something. So it could be a bow tie, it could be just a taper. We also have geometries where we don't need gold or plasmonics antennas, like I showed here. We could also have cavities, so as in proper cavities. So in this case, there will be no metal. There will be... So yes, they are different indeed. So we looked into bow ties as well. In fact, in one of the the beginning when I showed one of the schemes, there was a bow tie. It's not necessarily, depends also on the efficiency you want to have, the coupling you want to have. It depends, but you're right that there are different schemes that can be done, and for the moment we are not at sort of looking for the 0.1% that will give us more. So let's do simple things. So bow ties are more complicated to do than nanotapers, for instance.
Right. So another
but
question.
Sure.
Put to another question, just quick question. Time is running out. So if you want to develop quantum computing platform, so you will be putting many nanodiamonds on the same waveguide here, or how you are going to do like?
Yeah. So yeah. So the thing is, I didn't show, but these waveguides done by you can have an entire network of them. So
you will have
the
many
good thing is,
waveguides at the same waveguide. You will be putting many diamonds, many nanodiamonds.
both. So you would have complex structures themselves for the waveguides, and you can and you will have nanodiamonds, many nanodiamonds on say a given slab of photonic spectrum. So yeah. So the idea is to use the waveguide as an optical bus. So you need different nodes on the same waveguide. Yes. And we believe with our technique we can do that. The scalability is not too much of an issue. Always an issue, but less so here.
Okay, thank you.
Yeah, I had a related question.
Sure.
I'm Himatri from IIT Bombay. Yeah, thank you so much for the nice talk. Again, related to the previous question, so the results that you show, are you operating in the strong coupling regime? Because with a single NV center, it would be difficult to do that, right?
Yeah. So no, at the moment we're not at the strong coupling regime. So I mean we need more for that.
But would it hamper like getting photon blockade or something like that outside the strong coupling regime? Like getting a photon blockade for a single photon source.
Yeah. So this is also this is something else we look into. So indeed, to be in a strong coupling regime, or at least near the strong coupling regime, would be nice. But most likely we will need a different geometry or different system. So I talked about. So we would need a proper cavity. But you can do that. You can do all dielectric cavities, no metal cavities, in such platform. So we will probably. So this is something we're looking at, but there's a bit more work to do on that. So that's the second step.
Okay.
And that would be very interesting. But the trick then is that when you have a strong coupling regime, when you have a strong light matter interaction, that means by definition you're strongly coupled to the cavity. So you're not strongly coupled to an optical bus that would be nearby. So there are some issues here, which are the same issues that atomic physics people have been dealing with, that we will have to look into. But yeah, it's not simple at all. Yeah, sure.
Thank you. Thanks.
Sure. Thank you for the question.
Okay, so if there are no more questions, then I can open the chat box, and I see a couple of questions from students and beginning students perhaps. So sure. Let me read it out. The first question is what are trivial measurements? Okay, I see that this is from the last talk, related to the last talk. Well, by the way, trivial measurements are those measurements which give you the same result irrespective of what you measure on. So that is done then. Then there is a comment from Angel Rivas. Right. And finally, there is a question from a student.
So flying qubits to stationary qubits, right?
Yeah, exactly. Yeah.
Yeah, so I wasn't clear on this. So yeah, so what I mean by flying qubits are basically photons. So that's easy. So if you look into, you can still see my screen, right? Correct? If I take again, the quantum internet business, is that the stationary qubit, in this case, would be what Kimball called a quantum node. So in this case, it's pretty. I mean, it's easier to see. Is your atom in a cavity? So this could be your stationary qubit where you manipulate your two-level system, your single atom in a cavity, and then so that would be a stationary qubit, and then you can entangle between two nodes these two atoms through a single photon. and that would be your flying qubit. So that's what I meant by that. So in this case, what I have, in going back to the previous questions, is that you have, so locally you have a nanodiamond where you would have your stationary qubit. So in nanodiamonds, except as I said, there's a lot of work on manipulating the nuclear spins as well as the electronic spin. So this would be the what I call the stationary qubit. So you can make some calculation, so computation locally, some single qubit gates and more complex gates actually using nuclear spins. And this, at the end, the electronic spin will be coupled to a photon that will go away. That will be your flying qubit, and to the next node, to the next nanodiamond further. You can do entanglement swapping or entanglement swapping or entanglement between two nodes. That's what I meant. And so they're related by the photon. That's what we those stationary qubits, flying qubits.
So thank you very much again for a very nice talk. And now I think there is a break for about maybe 20 minutes, and the next talk starts around 5:30 India time. And so thanks once again, and a very good evening to you. Thank you very much.
Should I start? Subhasish?
Hello.
Subhasish, should I start? Professor Nayan?
Yeah, hello, sir. Good
Start.
evening. Yeah.
Good evening. I will start now.
Yes,
Because
sir.
it
Yeah.
is quite,
Yes, please.
okay,
please.
Prashant is also there.
Yeah, I am also there.
I
If we share.
yes, I am seeing, observing. Okay, Professor Prashant Panigai, he is now at ISAR Kolkata. He is a renowned physicist in our country, and he is doing research in the field of quantum information and etc. For a long time. I personally know him for a long time as physicist. I invite him to present his lecture in this program. Okay,
Thank you.
Prashant, you can start now.
Thank you, Devashish. And thank you. I'm really thankful to Subhasish, Narayan, and others, for the organizers to have invited me. This is a good opportunity where we learn from each other during pandemic period. We get to hear each other's work and hopefully learn something and move forward. So I'll be talking about in a very intuitive way about this multi-party entanglement, a geometrical picture. That is largely because you will see I had a lot of difficulty in understanding concurrence. So when we came here, my colleague Chiranjeev Mitra, he was quantifying entanglement of magnetic chains using concurrence. So that thing looked so complicated to me that I tried to understand in a geometrical way. And the result of that is what I'm going to describe. What I'll point out to you that by using this simple vector parallelism and area between vectors, you can actually quantify multi-part entanglement. So I'll just very briefly put this physics behind entangled states. Simplest example is our singlet and triplet states, which we encounter all the time. Hydrogen molecule, helium atom, where two electrons are in the 1s orbit. There, this Cooper pairs. There are classic examples of entangled states. And pure and mixed quantum states. Before these quantum states came, we had this light, this polarized light, partially polarized, and unpolarized light. Unpolarized light is, through this Jones matrix. If you remember, there are this 2 by 2, Jones matrices. So most of mathematics was already known in optics and in terms of polarization of light. So polarization of light, in fact, solves as qubit, as was pointed out to you in the previous talk, that you can actually generate single photons, and using their polarization state, you can actually realize this kind of quantum systems. So separable and entangled states are more sophisticated. In separable, for example, there are certain states which still carry classical correlations. Now, what I point out to you that those things can be all understood in a very simple geometric method using the so-called Wey's product. And what we have learned in high school about parallelism of vectors, isoperimetric theorem, the kind of things what makes the area between two vectors maximum. Those things are enough to understand the entanglement. After all, if you really think deeply about it, Hilbert space is a vector space. Therefore, it is not very surprising that this kind of vector space, the area and dot product, cross product, they will actually come in defining the entanglement property, which basically is non-separable vector matrices. We think in a complete way for the qubit systems or even qubit systems. The same has to be carried out a bit more carefully for continuous variable states. Therefore, as you may realize, beyond Gaussian states, we have not made much progress. So hopefully the kind of thing which I am describing to you would give some lead for continuous variable states beyond Gaussians. Then I'll also point out, this complementarity in two qubit systems. There have been recent investigations about, other kind of correlations which are present in two qubit and multi-qubit systems. For example, complementarity is one thing. If you see with Dr. Qureshi, he has done quite a bit of work. So that will be related to this kind of things what I'm talking about. Then multipartite entanglement also I'll touch upon. And then point out to you that when you go to 4 qubit systems, And of course, you did systems, there are a lot of new things open up. Okay, so this entanglement is what is due to Schrödinger, who has come up with many interesting ideas about quantum mechanics. Continuously, Einstein was the person who was baffled by quantum mechanics and posed very serious questions. And many of those questions challenged people like Schrödinger and Bohr and others. And Schrödinger particularly has been credited to bring a lot of these kind of interesting features like entanglement and steering. Many aspects of it we saw it early. And some of those things we are now using for technology. So therefore, now, so how do you prepare it? For example, in the 80s, when this gate versions of quantum computation came out, it was realized that Hadamard and control lot, they are sort of universal, and single qubit and 2 qubit gates. Hadamard is the one which creates superposition. For example, 0 is taken to 0 plus 1 by 2. And note, without superposition and control lot, you cannot have entanglement. So you need superposition. There also are interesting open questions. For example, here is a simple circuit. You can play around in IBM, quantum computer, and you realize, just check it out, how much of error comes in, which gate has more error. For example, control lot you expect involves 2 qubit will have more error. Now, which out of those 2 qubit, some of the qubits will have more error, some will have less error. So these are very interesting things. You can take this very simple thing, create a Bell state in IBM quantum computer and try to see how reliably you are able to create it. Now here, for example, what are the questions you can ask? See, we all know that if it is entanglement, it has to be 0 for separable states. Maximally entangled state, it has to match it. Now, in between, there are very many measures of, entanglement, particularly for the mixed state, but nobody agrees between these two, separable and maximally entangled. So therefore, that itself is a good question. And how many terms? For example, there are 2 terms here. When you go to general setting, if you need superposition, because without superposition, you won't have entanglement. You need superposition. Question is how many? How many of terms we can give you maximum? You can, in this case also, you can play around. For example, if you go to the matrix version, I'll show you as it goes down. So, for example, what is this paradox about? Even now also, there are deeper questions involved. So, point is this, that at some point, which is at the middle, you 2 particles were created out of one source. It could be a single photon giving rise to, or a given pi naught decaying to 2 photons. Or, for example, electron-positron emission from a photon in the background of a nucleus. As you know, a single photon cannot generate it. A pi naught can decay into 2 photons. There are sources from which entangled pairs will come out. And in nature, most of these things are created in singlet or triplet state. So because of angular momentum conservation, which I have emphasized here, angular momentum is conserved, because of which this correlation is preserved. Unless something else comes in between, this conservation of angular momentum, which keeps track of this entanglement. So this has to be kept in mind. This, entanglement surviving for longer duration is basically because this angular momentum is a conserved quantity. So therefore, in practical systems, when you would like to preserve entanglement, one should be very clear that the scattering and other processes should be controlled so that this conservation of angular momentum is still intact. Very good. So now, so the moment the positive is this, that when you are at A and B, the correlation is preserved, and the moment you measure, for example, you emitted 2 photons in the singlet state. The moment you measure at A, if the state is up, instantaneously the other fellow is down. So this is this non-local correlation which bothered Einstein. Now the question is, how non-local is it? Is it instantaneous? So as you will see, it was realized very early on that information still travels at the speed of light. And you will see, for example, teleportation have been done. You will see that unless the classical information is communicated through a local channel, through so-called classical communication at the speed of light, the teleportation is not effective. So therefore, information is not traveling at the speed faster than light. It is not instantaneous. It goes at the speed of light maximum. So there are puzzles like that, before about this non-local correlation, which exists even now also. So now main point is that this puzzle was converted into technology in 90s, thanks to teleportation, dense coding, many other things. So now these things are coming in handy, this action at a distance. But the thing to keep in mind for practical application is that these correlations in our practical systems happens because of certain conservation concepts, like momentum conservation, angular momentum conservation. So therefore, in realistic systems, one should be careful so that this kind of interactions which violates or to lead to violation of this kind of conservation law should be should be one should avoid it so that this is preserved for longer period. Now when we talk about density matrix, much of which we knew in the context of optics. So for example, polarization optics particularly, this you have now pure and mixed state. Pure state in case of optics was the thing which was lying on the Bloch sphere, polarization state. Now, in our case, for example, is the wave function for a general qubit. It's a column vector with alpha beta, mod alpha square plus mod beta square is equal to 1. Now, if it's a mixed state, you cannot represent it as a state vector. You have to have a matrix. One good thing is that when you write in terms of psi, it is invariant under the phase transformation. So therefore, this fact that wave function is measurable modulo over a phase, that ambiguity does not arise when you go to the density matrix. And of course, at the hand of von Neumann, density matrix are used to provide a description of statistical mechanics as well as quantum mechanics. So because of which the terminology which we use, this entropy, other things, is due to von Neumann. So density matrix that way is a much powerful method as compared to state vector itself. Now, after all, whenever we do anything, keep in mind that we are dealing with matrices. Now it's a positive semi-definite and Hermitian matrix. So if it is pure, rho square is equal to rho, and trace rho is equal to 1 is because of normalization. Psi mod psi is equal to 1. Mixed state, for example, trace rho square is less than 1. Now, of course, you cannot in this case describe it by wave vector psi. So now, okay. So now, if you go, for example, if there's only one term, so suppose somebody gives you a matrix rho, if by speed decomposition or by some other method, you can write it as only one term, then obviously it is a pure state. If more than one terms are present, then only it is a mixed state. Now, in case of mixed state also, there are two classes of states. For example, the last one which I have written here, if these PIs are all positive numbers and they are out of 1 obviously, then it is actually is not an entangled state. Where do you see this kind of things? Classic example is thermal state. So there are multiple states, for example, which are excited because of heat. And so, for example, weight factor is exponential minus E by KT. All these are positive numbers. You add them up to 1. So these kind of things we always encounter as thermal states. Those kind of states, of course, are not entangled, but they are mixed states nevertheless. So this more formally are represented by this kind of PIs, where all the PIs are real, they are of 1, there's ordering, P1 is less than P2, P2, P3, like that. So you can give yourself mental picture of thermal states with excited states having less and less weight. So now, so as I was mentioning to you, that this when you go to this kind of matrices we have encountered in case of Dirac spinors. And of course, for example, this object 100 is the one which represented a particle with spin up. This object 0001 was an antiparticle with spin down. Now, of course, here in case of light or in electrons, we are representing in a different way, two-particle state. But when you can talk about intra-particle, 2 degrees of freedom of one particle being entangled. So there, if the classic example is to think in terms of Dirac fermions, where treat it as a column vector, and if these two factors are entangled, for example, here 1010, this stands like, for example, particle state. This is like, or another particle state. So you can, in fact, this kind of thing goes over to intra-particle entanglement also between 2 degrees of freedom. Now, for example, one classic case is graphene, where there is valid degree of freedom, and there are 2 manual minima. Those two fellows can be entangled. People are in fact talking about those kind of things. So this same kind of mathematics goes through there. Oh, now, okay. Now you add them up, you find this state, and this is maximum entanglement. So actually, if you really ask me, I was wondering all the time, how come that if you add them, if there is, location of 1 is very important. If it is like 1100, you can convince yourself it is separable. So this location 1, 0, 0 plus minus 1, then 0, 1 plus minus 1, 0. The location of 1 is very important. And the moment you add one more term, for example, for normalization, you have 1 by root 2. If you have something like 1 by root 3, 1, 1, 1, 0, you can check that it is still entangled, but base entangled. So the question arises, how many terms? In this case, for example, you can actually show as one has shown, 2 is enough. But in general, what is the summation or how many superposition is required? I don't know if the answer is there in general. So entanglement itself has many interesting questions dealing with matrix properties. Now, physical systems, for example, if you go to topological insulator, you will find out that orbital and spin degrees of freedom will be entangled. So the space, higher dimensional space, may come due to partly spin, partly due to orbit. So that is where many interesting things happen. For example, there you will find out when they become separable, there is phase transition. You go from normal phase, to there are this topological insulator phase, insulating phase, and the other phase. In fact, we have a research paper showing that when this fellow is disentangled, you go from one phase to another. So this same state in context of degrees of freedom involving spin and orbit, or same degree of particles, say 2 different degrees of freedom, are more interesting. Now, when you talk about separation, you can go to a general scenario. Now, bipartition means you can divide into 2 parts. Hilbert space dimension could be different, or number of particles could be different. Now we are talking about qubit only. So division is total is m plus n, capital N. You can divide it asymmetrically. So essentially, you are looking across 2 partitions. If it is separable, you should be able to factorize in this way. If it is not, then it is entangled. Now, okay, so that is the simple examples that if it's a pure state, for example, only one term here. Now, if it is take a density matrix, if all the fellows are present, you can convince yourself that is actually pure. But due to some reason, if the odd diagonal terms are missing, look here 1 1 0 0 0 0 1 1, which is known as coherence, for example, in optics of diagonal terms. When they're missing, this is an example of a mixed state. Okay, and in fact, if you look at it, it's maximally imaged because the density matrix is half 1 1. There is no information. So now this in fact can be thought of as a classical mixture. Completely unpolarized light is represented by the state. So okay, now so this bipartite quantum entanglement, one can define, for example, 3 qubit. You can imagine that first fellow is the single qubit, the other fellow is 2. Now, why I'm saying that? Because my approach which I'll be taking here will depend on measurement. So, for example, if this Alice has a single qubit state, you have to consider measurement basis of Alice, which, for example, one could be 0 and 1. Here, it could be computational basis or it could be entanglement basis. For example, computational basis, there will be 4 of them: 0 0, 0 1, 1 0, and 1 1. So, when we describe the Hilbert space, and the way I'm going to deal with it, this plays a key role. So, therefore, the basis state should be taken depending on the dimension of the bipartition. Okay, so now, okay, so any entanglement, descent measure of entanglement should satisfy many properties. So, one of them is that separable, it should be 0, as I mentioned. It should be maximum, for example, whenever it is maximum in time. That is this thing is here. Now, as I told you, here also there are a lot of interesting questions that in between there are so many different measures of entanglement in general, and none of them coincide, particularly for the mixed state. That now, what is the meaning of then these other states? Of course, one thing is what kind of quantum tasks they can do. Can they do teleportation? We know very well that, for example, maximum time states are required for teleportation on dense body. So, this is a deep question to understand what is the physical element. At least in physics, we know all this, for example, singlet, triplet, those kind of states. They are, because of symmetry, total wave functions should be symmetric or antisymmetric. So, therefore, triplet, singlet states are symmetric, antisymmetric states. The corresponding special part satisfies the other property. But in general, you can imagine like a big molecule where, the atoms could be of different kind, yet there could be entanglement. So that is where these more general kind of things will come in. So it's worth thinking. For example, if you look at, for example, wave functions of proton, you would realize there are very many degrees of freedom. There is spin, there is an orbital angular momentum, there is, for example, color, there is flavor. You have to anti-symmetrize in all these spaces. So if you go and look at Custom Huang's book, it gives, for example, proton's wave function, and you'll find out it's actually highly entangled. So many of the physical properties, for example, magnetic moment of neutron, or for example, if you look at the distribution of angular momentum, claim is that gluons carry half of the angular momentum inside a proton. So one still have many questions which entanglement be able to answer, and particularly in many scenarios, it's still not very clear, which way physically this entanglement manifests. So of course here we are dealing with very simple things that this is a measure, and that is what whatever will come up, you should satisfy these things. Now you see the second thing is this, that your local operations will not affect it. Now if you really think about it, mathematicians, for example, would say, if you look at a 2-qubit system, it is a Hilbert-Space dimension, it's a column vector with 4 entries. So now the symmetry, there is SU4, the local symmetry, there is SU2 cross SU2. So SU4 mod SU2 cross SU2 is a space where this entanglement lives, and that is called Grassmannian. It has very many properties, very difficult, unless you have a good mathematics friend to understand entanglement. Persons like me, for example, I need a mathematics person to help me out. But you can see this business of this that local operations, local transformations should not affect it, make this space highly non-trivial mathematically. Similarly, for example, next one is local operations and classical communications should not increase. This is also quite non-trivial. For example, you can show in the presence of a time-like chord, you can actually, through local operations, increase entanglement. So therefore, you can actually come up with non-trivial examples where, time-like chord, for example, if they exist, with this property one can show experimentally, then it will sort of violate physical intuition. So many of these postulates which we have listed here can still be checked in unusual conditions. Okay, so lastly, it is a convex function. All right, so the concurrence is the method which people have been using, and it is this complex nature of this expression where this object is defined as maximum of 0, and this difference lambda 1 minus lambda 2 minus lambda 3 minus lambda 4, where the lambdas are the eigenvalues of this object. Rho tilde. What is rho tilde? Rho tilde is you take rho star pass, apply sigma y cross sigma y, local operations. Now, some similar thing I have seen in the context of that when you go from particle to antiparticle, charge conjugation. Okay, so why this matrix appears here, and rho tilde, the eigenvalues appear in concurrence. If you ask me, even now also I don't have more physical intuition. That is one reason, particularly for pure case, for mixed case. There is one reason why I was looking for a geometric understanding of entanglement. Unfortunately, for pure state, it comes up in a very simple way, that 1 minus trace rho a whole square. So that, of course, is still not very clear why it should be like that. But at least the density matrix would have all the information, and if you take rho a, its eigenvalues are trace is the invariant quantity, you can describe in terms of eigenvalues. So rho a eigenvalues I can imagine. For this complicated expression, I still don't have much intuition, and my understanding of entanglement started from there. All right, so now how do you compute, for example, Bornemann entropy? But you have to take reduced density matrix. So you have now this object rho AB, which is entangled. Obviously, there is a non-local correlation existing between them. So if you take partial trace, you sort of integrate out either A or B, it leaves a signature because these two fellows are not entangled, entangled. Therefore, if you integrate out one fellow, which is like partial tracing, there is soft signature left on the particle A. What is the signature? The signature A is that this rho A in some sense is a thermal state. Or you can see here, I imagine as a physicist like thermal thing, here it is like in a mixed state. So this mixedness of particle A is getting induced by particle B because of this kind of entanglement. So it's a very physical manifestation. You can actually think that maybe the origin of mixedness on polarization getting on fully polarized to partially polarized because of this entanglement interaction with the environment. So, so that way, for example, statistical mechanics or other kind of things, one can really look up in a different way through this lens of entanglement. Okay, so now, so I will now talk about this mathematics of waste product, using which one will be able to give a geometrical picture. So we are all familiar with core area A cross B, but when you define A cross B, then you find that you have to introduce a tensor epsilon ijk. So you need a third dimension. But it was very soon realized that you don't need a third dimension. You can live on the plane. Through this waste product A with B, you can actually define it on the plane itself. There is no need to go to any third dimension. What do? You expand A in terms of basis, EI and EJ. This EI with EJ, that form a basis, another set. So this A with B can be defined like, it has a, through this cross product, you can actually define these things. If you look up some nice book, you can actually see there's a connection of this object for your own understanding through cross product. But, EI with EJ is defined on the plane itself. So the whole thing lives on the plane. So now with this, I will not be able to go into deep mathematics behind it because it's very useful thing, waste product. You can use it to simplify many things in physics. Of late, there have been number of seminars and other kind of things using this waste product to describe physical laws. Now they are parallel, means A with B is equal to 0, like your cross product. So many of those properties goes through. All right. So now this, as I mentioned to you, this entanglement can be understood in a very simple way by looking at vectors. And if these vectors are parallel, you will see that there is no entanglement. If they are perpendicular, they are entangled. Now the question arises, when is this entanglement maximum? So that interestingly has a connotation and connection with isoperimetric theorem. Namely, when there are two vectors A and B, what is the maximum area between them? So now, so this is basically our students here. They went back to their high school algebra, and which I have completely forgotten. Now these two conditions are given. For example, in our case, vectors are all normalized. Now because of which magnitude of A and magnitude of B, for example, qubit, both of them are normalized to 1. And then, in our case, for example, A mod square plus B mod square is equal to C. See some constant. So these kind of conditions, when they are given, particularly in our case, for example, for inverse space, it's qubit, mod A is equal to mod B, and this kind of thing is satisfied. Now, so there are, so the maximum value of A with B corresponds to vector A and B if they're orthogonal and magnitudes are same. This is this isoperimetric theorem, that the magnitudes are same and they should be orthogonal. So you can easily, intuitively, immediately think and
Possibly there is some network problem.
Hello?
Narayan, is there any problem with Prashant?
Hello? I am trying to reach Professor Panigragi, so kindly be there.
Okay, okay, okay. Actually, heavy rain at Calcutta or maybe at Kulani also.
Yeah, Professor Panigragi will be continuing shortly, so he has some network problem. He will be connecting in a minute or so.
We are not getting the share option.
See, Narayan, we are not getting the share option.
Sir, yeah, 1 second, just I will tell the volunteers to do it.
Sure, sure, sure. It's now audible. Is it okay now?
Yes, yes.
Narayan, can I speak?
Yes, sir. Yeah.
Yes, you start.
Yeah, yeah. Okay. Sorry, there was this.
No problem. Yeah, actually, I observed at Calcutta heavy rain is going. So it
okay.
may be
So,
at your place.
So I have, let me quickly go over this one. Whatever. Yeah. Okay. So now we explained that physically the meaning of taking trace over one of them. Now, as I told you, using waste product, one can actually define this entanglement as through this isoperimetric theorem, that if the two vectors have same magnitude, like which is true for qubit, and there's a condition on their mod square, then entanglement becomes waste area becomes maximum, provided they're orthogonal. So now this thing can now be extended to a general scenario, because for example, if you have a multi-qubit system with dimension n, all qubits, you can divide into any two parts. So this For example, you can in this part, the first part, you can define a Hilbert space with this kind of dimension 1 to j. It's a product space. Now the other fellows are left intact. So when you look at the projection along this basis, this is like a measurement. So what happens is that from the wave function, the rest of the thing gets projected from j plus 1 to in. So you can this way imagine that this side, this Hilbert space, you are already projecting. The rest is there. You can look up just like we did. For example, the moment you take the trace over 0 and 1 on Alice, Bob state shows a mixed state. So same kind of thing you can imagine in a multi-qubit system. So therefore, for example, explicitly, if you go to a 2-qubit system, a general state is of this kind with ABCD, which could be complex. Now, you can see here that if you are projecting along A, then the thing that remains is A0, 0 means A0B actually. This is 0B, right? So the other fellow is A0A and plus C1A. You can see here, this is actually B. So now that is the state which is here. Now similarly, you can imagine if it is 1, then just take 1A, whatever remains, 0B and 1B is the state of Bob. So that is how you can go over to a general scenario. So now, so this is a, then what you find out is that through the waste product of this, phi I psi waste product with phi j psi, you could actually define square of this, which describes the, the general I concurrence or the waste product. So, formal thing you have to sort of massage it a little bit, but the mathematics is fairly simple. Separate out in 2 parts, find out the basis in one case. For example, here the basis is phi I. Now, so you can imagine like 0 and 1, in this basis, whatever is remaining, because of what is the waste product, that is the measure of entanglement between A and B. So as simple as that. And in fact, in case of 2-qubit or multi-qubit, this whole thing lies on a plane. Okay. So now you can also physically imagine that, for example, in terms of if they are separable, that basically would imply these vectors are parallel. So for example, if you are finding that this one vector is, when you measure along A direction, if it is B and this object is this, and along A is this 2, then this should be separable provided these 2 vectors are parallel. These 2 vectors are parallel means A by C is equal to B by D. And this scenario holds good in the multi-party case also. So to conclude up to here, separability of 2 subsystems implies those 2 vectors should be parallel. Now, entanglement means that they should not be parallel, and if the entanglement is maximum, the area should be maximum. So, then there are a lot of identities involving, for example, this, if you look at our papers, Lagrange, and quite a Brahmagupta identities and other kind of identities are involved, in which you can actually massage these expressions and come up like Schwarz inequality with some compact expressions of entanglement. So geometrically also, you see this very simple things like these 2 vectors are parallel or not, you can actually define entanglement and separability. And this we have also currently checking holds good in a multi-qubit scenario, continuous variable states also. So now this scenario, you can actually take it down to any of this, dimensional Hilbert space. So more generally, this is the area, and all this for the qubit case, any number of qubits, the whole thing is only defined, on a plane. Okay, so now you can actually show that in general, very interestingly, that you start with general state. Once you implement this equality and orthogonality, you can actually massage it, and the whole thing boils down to a Bell state. Okay, so and the expressions which I mentioned earlier, that this in case of 2-qubit, and that 2 1 minus 2 trace to rho square you find here because of this expression. Okay, so now as I mentioned to you, there is another object which has come up, particularly if you look at the works of accuracy, is so-called complementarity. So this actually happens because if you take the density matrix, you can actually show that this kind of there are elements. For example, diagonal difference is called PA, called predictability. So this is the difference, basically sigma 3. Similarly, off-diagonal elements are present, and whole thing, remember that trace rho is equal to 1. So these things all add up to something. Here, although naively it is an identity, physically you can actually measure them. For example, this object is basically concurrence, which is two particle property. So here, this object is like a single particle property. So this kind of relationship connects them. In terms of polarization optics, you can also understand them. So now, this triality relation between, you see, the single particle, this concurrence is entanglement. Now, coherence is here, predictability here. These are single particle properties. Amazingly, that these kind of things satisfy their identity. Mathematically, quite simple coming from property, but when you measure, these quantities, they appear to be separate quantities, but actually they are connected. And the nice thing is that you can generalize these kind of things to more than one qubit. Similarly, for example, monogamy relationship. Also, you can actually come up with same kind of ideas. And for example, go to different kind of bipartition. Look at the absolute the type of vectors what you're looking at. Here, for example, 0, 0, 0, 1, 1, 0, 1, 1. Here 0, 1, and you find out that there are certain identities which arises because of multi-particle nature, and monogamy is one of them. So, because of lack of time, I will not get into details. I'll refer at the end to some of our articles. But indeed, it is true that you can actually have a geometric understanding of monogamy. Furthermore, when you go to 4 particle, you realize that conventional definitions which are given in the literature, there are some problems. Whereas through geometry, you can actually define a proper relationship. So, and the kind of things which I pointed out, that entanglement, coherence, and this predictability, those kind of things generalize. For example, for Q-treat and other kind of things, you can also generate a similar kind of idea for them. So this is the waste product kind of expression in terms of area for this conference across this bipartition. The nice thing to emphasize here is that all these things are defined in the plane because it's a qubit system. So, for example, this Kaufman-Kundl-Wurtz inequality actually follows from a geometric kind of understanding of inequalities in terms of area. Okay, so again, I will not get into details. I will refer our you find out, for example, in case of GHS state, it's a natural entangled state. Now, and the main point is that it is a measurement-based approach because you look up divide the set into 2 parts, find out the basis set in each of them, and project it, and then accordingly you have certain kind of area identities which is basically coming because of measurement. In that sense, it has a leg in experiments. And one thing I would like to emphasize that when you go here, when you project this normalization, you should keep in mind, right? So tangle you can explicitly compute for W state, for JZ state, and for JZ state you find it to be 1. And once more, I would like to emphasize that all these things are actually defined on the plane. So for qubit, all these identities are in terms of areas in the plane. Okay, so for W state also, for the sake of completeness, I'd like to point out that and the identities which I was mentioning to you are again this kind of area additions, which happen to explain the tangle and this Kaufman kind of properties which monogamy which entanglement shows. So I, without much generalization, I would point out that there was some problem with the entangle which have been corrected, particularly from 4 particle onwards. So they are just formal expressions, and I will not get into any more details. So main point is that a directed area vector is the geometric language through which this kind of correlations can be understood. Okay, so now also we have understanding for Q-treat system. Certain things which were pointed out in this nice paper by our colleagues from the Bose Institute. You can actually have a geometric understanding of that, both in terms of parallelism. So I will not get into details. I am just going to give you some references. This is the first paper, Bhaskar and myself where this Lagrange identity, the Mobius identity was used through a product to quantify it. Subsequently, Shreya did quantifying parallelism for the n particle case, where this beyond 4 particles there are some problems with entangle, which was pointed out. Now, very recently, our Avinash and Nitish have done these kind of things. Isoperimetric theorem came out through there. I think these are all under consideration. So I will stop it right here, and I will thank you.
Thank you, Prashant. Very nice lecture. Now it is open for questions. Tanmay, you can speak.
Hello, can you hear me?
Yeah.
Sorry. Yeah. So my question is, so my question is that I didn't understand your point about conservation laws and the entanglement. I mean, sort of seeing the correlations. Like where does that? I mean, does that come in because of a theorem or formalism, or is it derivable? Or I did not understand that point. Could you please re-explain it?
Can you emphasize which point?
So, like fairly early in your talk, you mentioned that I mean, one spin up if with one. So over there, you're talking about angular momentum conservation. Now there is also, it could be other kinds of conservation laws, right?
Right.
So, but why is there? Where does that necessarily come in? Like, I mean, you at some point I thought you made it sound like there will be a conservation law associated. I don't where that will be the case.
It's a good question, very good question. So, at least for the that's a very good question. See, singlet, triplet, those things are actually broken up in terms of angular momentum. Here we can talk about angular momentum conservation, those kind of things. But when you talk about 0, 0 plus minus 1, 1 by root 2, they definitely are not angular momentum basis eigenstates, right? So that way, but they are maximally entangled. That way, what you are asking, can one think some kind of conservation laws? I have not really thought about it. Okay, I will get back to you. So that's a good question. Certainly, I don't see offhand, any conservation there, because 0, 0 plus 1, 1, there is no angular momentum. But let me think about it. That's a very good question.
I mean, one could perhaps think about an arbitrary or observable and reverse engineer that, oh, okay, fine, in this case you have this being conserved, or something like that.
Yes.
But
yes, I really appreciate. Very good question. I really don't have the answer.
But I don't think you can get necessarily Noether's theorem to say that it's...
Yes. We can't. So that is the thing. Sometimes we just offhand make this kind of statement, like what is true for singlet triplet in general true may not be correct. I'll keep that in mind. Thanks.
Sure. I mean, I'll write you an email about it if you're okay with that. Okay. Yeah.
Any other question?
Prashant, how you can you plan an experiment? Can you indicate how to do experimentally? Any idea? Have you discussed with someone?
No, I have not. But so you
like
are saying
this
that
parallelism seems to be very simple, orthogonal and area maximum. So how you can check it experimentally? These are orthogonal and area is maximum.
Yeah. So I think what you are saying is that for example, if tangle and all those things, can one measure them? Through this geometry picture,
density matrix, we can find out the density matrix. That's fine. Then you can calculate concurrence, angle, all those things. But this orthogonality of these vectors and this maximum area, how you can check? Like suppose you have qubit, two qubits, like we make with OM. So suppose you have two qubits and you want to verify whether they are maximally entangled or not. How I can check their orthogonal and area?
I think RPG, I have one answer. See, this local property, like coherence and here predictability, See, there was one, there was one identity involving entanglement, so coherence plus predictability, right? That was it.
It is there, Tabis has written. Tabis has done has written that paper. Yeah.
So that may be useful because that may be useful.
But it's not directly related with what you talked about, this isoperimetric thing. This
No, see, for example, what I showed is that because of that, we have a tight condition, no? That this concurrence plus predictability plus coherence was 1, right?
So that is coming because of that. Okay, fine.
Right. So that we can discuss about it. That's a good point.
Okay, fine. Yeah. Thank you.
Any other question?
I would make a little question/comment.
Oh, Richard, how are you?
Yes.
Hi, Prathanta. Nice to see you, or to hear you at least.
Yes, Richard.
So nice talk, Prathanta. I really enjoyed it. It made me realize something that I probably should have realized 100 years ago. And I wonder if it's obvious to everybody or if, I don't know. Anyways, what occurred to me listening to your talk is that we always think of entanglement as something rather esoteric, but it's actually, I guess, a property of say an atom in an total angular momentum eigenstate. If the atom has orbital and spin angular momentum, then a total angular momentum eigenstate is actually an entangled state with respect to the spatial degrees of freedom on one hand and the spin degrees of freedom on the other hand. Is that, I mean, I think that's true. I would just like to get your comments. Is that an interesting observation or well known to everybody except me until your talk, or?
No, it is not well known. Definitely not well known. And that observation is correct. Only thing is that the effective degrees of freedom should be describable by finite dimension. Like for example, in this thing which we dealt with topological insulator, this orbital degrees of freedom, they formed a finite dimensional Hilbert space. But the moment you get mixed up with finite and infinite dimensional Hilbert space, then the problem arises. But otherwise, you are right. The effective Hilbert space point of view, this kind of correlation could be between orbital and spin, and the measure is same.
Okay, thank you.
Thank you, Rich. How are you?
Very good, but we can talk offline.
Sure. Thank you.
So let's thank the speaker again for his nice talk.
और एक भेज दिया इसका मैंने एक SPCM तुम्हारा वाला था, एक बिमलेस का, दोनों कर दिया था मैंने.
Okay, thank you.
हमारे SPCM एक क्यों भेजे थे, बिमलेस भेज, दोनों मैंने क्या सही भेजा है. हाँ.
Sir, there is a question in the chat.
Yeah, can you let me just read it out? Yeah.
Yeah, I will read out for you.
Okay. Definition of waste product.
Yes, sir.
Waste product is somewhat like a cross product. So if you send me an email, I can send you a very simple article which is readable, with an American Journal of Physics article. You can, through cross product, you can actually define waste product. If you are familiar with cross product, you can pretty much translate that to waste product.
Okay.
So because you send me an email, I'll send you one nice JP article. Yeah, Devasis, I am through.
Thank you, Prashant. Okay. So our next speaker is Arun Poti. He is a very renowned scientist in the field of quantum information and computation in India. Actually, he is one of the pioneer worker in this field in our country. He is doing research for a long time. He has received many awards, etc. And last year from the Stanford's this collection, he is one of the very most Indian scientists who is in the top 1% in general physics. So, and he is also very good friend of myself. I know personally Arun for a long time. I request Arun, you are hearing me? Arun?
Yes, yes, I'm here. Yeah.
To give his lecture on classical communication with indefinite causal order. Okay, Arun, you can start.
Okay, thank you, Devashish. Let me start sharing my screen. Can you see? Are you able to see
Yes,
the screen?
yes. Now you can go with the slide mode.
Is it better now?
Yes, it is better.
Okay, so let me thank Subhashis for organizing this conference and inviting me to this. So today I'm going to talk about classical communication with indefinite causal order for n depolarizing channels. So this work has been done in collaboration with one of my earlier postdoc, who is now in Poland, Sajim, and so also Michael also involved from Poland also, and I had a visiting student from Ajay Bhopal. So we started this work something like 2 years back, and this year this got published. So I'm going to tell about this today. Not going down, so if I make full screen, it's not going down. I don't know why. So let me redo again. So now it's going down. Okay. So here is my plan today. So I will tell you about what this indefinite causal orders are in quantum mechanics, and then I will tell you how to send classical information using this indefinite causal order, which are often also called quantum switch, and how this can enhance your classical capacity in quantum communication channel. And then I will talk about various combination of cyclic and non-cyclic causal orders, and finally I will try to conclude. Okay, so quantum superposition, as we all know, is one of the key feature in quantum world, because that's the starting point of understanding quantum mechanics. When you think of a Young's double slit setup or any variation of that, you say that in quantum mechanics, if you have two or more possible states, then it is also true that the quantum system can remain in a superposition of all those possible logical physical states. Okay, so all this over the last 100 years or so, we have been using quantum superposition for quantum states. But what about physical processes? Can you really superpose physical processes? So, in classical information theory, it is assumed that information carriers are deterministic and the transmission lines are used in a definite configuration in space as well as in fixed time. I just said till few years, maybe 2-3 years back, this quantum information protocols, all we are familiar.
what we do is we assume that channels or physical processes they maintain a specific order in space and time. But recent progress, starting from Brooknet to Chirivella group, they have shown that quantum theory allows configuration where channels themselves are in superposition. And moreover, recently it was realized that this superposition can exist also in the order of different channels. And that scenario, what we call as indefinite causal order or quantum switch. So this is a typically you can imagine like a black box where quantum information is sent as an input and that undergoes some physical process which is in superposition of different order, and then you get some output. Okay, so and then you analyze the output and you see that something extra, something beneficial you can get through this black box compared to what it would be otherwise if you don't have this superposition. Okay, so in quantum mechanics, the information processing tasks are performed in definite order, but in quantum switch, as I said, you can allow superposition which can exist in different order of channels, and that gives rise to quantum advantage. So this was first realized by Chirivella and his group that a non-zero classical communication using two completely depolarizing channel can help you to send non-zero classical information. So typically what will happen is if you send a quantum state through a completely depolarizing channel, you will end up with a state which is like I by d. Okay, if you send a qubit, you will end up with a state which is identity by 2. Okay, completely random state, and that has no information whatsoever about the input state. But if you have this quantum switch, you can achieve non-zero classical information, and also you can achieve later on. Other groups have shown that you can also achieve non-zero quantum information communication. So ordinarily, if you use quantum circuit with this completely depolarizing channel, that cannot provide any quantum advantage even if you use that several number of times. Okay. So over the last couple of years, a lot of development has happened. So I will try to highlight some of them. It's not a complete list, but I will try to focus some of the interesting applications of quantum switch. So this group in particular, they have shown that you can use quantum switch which can reduce communication complexity. And again, Chirivella group and this group, they have shown that you can use this indefinite causal order. It can improve channel discrimination. And Chirivella and the area, this group, they have shown that you can use quantum switch to have a better quantum computing scenario. And so these are not just theoretical possibilities, but actually people have actually, they have realized an experiment like in 2015 and also 2017. And these two groups, they've also tested these proposals in experiment. So continuing along these applications, Chirivella and Manik and I think Guru Prasad also involved in this work. So they have shown that quantum communication advantage you can establish using this indefinite causal order, and you can also that non-zero quantum capacity is possible if you use this quantum switch. And with one of my previous students, we have shown that you can use this quantum switch in a noisy channel, and you can enhance the teleportation fidelity, which is otherwise not possible, if you don't use this quantum switch. And also with my student Chiranjeev, we have shown that you can design a quantum thermometry using this indefinite causal order, and that allows this probe both interaction using a quantum switch and that enhances your thermometric precision. And very recently, Vedral and his group have shown that you can use quantum switch in region of quantum refrigerator, and which is actually very useful compared to what it would be otherwise. And in another work with one of my students, we have shown that you can create quantum coherence at a distance location, at a remote location, using this indefinite causal order. If you don't use, you will not be able to do the same task. And Priti Parasar and a group, they have shown that you can extract some amount of work from thermal channels, namely this phase flip and generalized amplitude damping channel, which leads to enhancement of final free energy if you use this quantum switch. If you don't use, then these kind of claims you cannot do. Okay. So let me try to tell what exactly these new ideas involved in this independent causal order. So imagine that you have two channels, say lambda1 and lambda2. So when I say channels, essentially they are completely positive trace positive map, so CPTP map. And there are two CPTP map like lambda1, lambda2. Okay. So next what you do is the following, that you have this input row, and you assume that there is a control qubit. If it is in state 0, the input state row first goes to the channel 2 and then it goes to channel 1. And next time you assume that if the control qubit is in state 1, the input state, that is the state row, passes through channel number 1 and then number 2. Okay. So if that is the scenario, then you can ask the following question: that what will happen if you have a control qubit which is in a linear combination of 0 and 1? Okay, that is something like this: 0 plus 1 with equal amplitude. Okay. So what people have shown is that if you assume that these two channels are completely depolarizing, then obviously at the end you will not get anything. But if you use this input state like this, then you can achieve non-zero classical communication. So that is the magic of this quantum switch. Okay, so so what I said was answered in the context of two channels. Now what we want to address in this work is the following: that can we enhance the classical communication if you use n channels? And in particular, is there any hope that we can have some kind of perfect transmission of classical information if you go on increasing number of channels? Okay. And second question is the following: that can we achieve substantial gain in classical communication rate with an optimal number of causal orders in the quantum switch? Okay. So these two questions we would like to address, and actually we have answered, that paper that I showed in the beginning. Okay, so let me first tell you what happens when you think of a quantum switch with two channels. Okay, so to perform information processing task, we need a completely positive trace periodic map lambda, and that allows this cross decomposition, which looks like this. And suppose you have two channels and you allow them to superpose, as I said in the beginning, and assume that these two channel lambda 1, lambda 2 have this cross decomposition like ki1 and ki2. And then what will happen is the input state, which is your now this system of interest and plus this control qubit, they will undergo a super map kind of thing, which is again a CP map, but it is composition of these two channels, and this cross operator wij, they look like something like this. So the projector tensor with ki1, kj2 plus projector onto 1, tensor with kj2 and ki1. So notice the following thing, that if these elements ki and kj for different index I and j, that is I not equal to j, if they commute, then what will happen is this ki1, kj2, you can write as kj2, ki1, and you can take this outside. So this cross operator wij will look like 0, 0 plus 1, 1 tensor with ki1, kj2, and you will essentially end up with I tensor ki1 and kj2. So what will happen is the scenario will boil down to just first applying the channel number 1 and then 2, or vice versa, it doesn't matter. Okay, so nothing new is going to happen. So the essential element here is that the Krauss elements corresponding to the channels that we are going to superpose, they should not commute. This is the key insight one should remember when one thinks about this superposing different channels. And then you see the magic happening. So what we do now is we try to generalize this superposition for n channels. In particular, we try to imagine there are n completely depolarizing channel, and try to see what happens under such scenario. And if you extend this formalism to n channel, you can write down this Krauss operator for this n channel, and they look like this. The projector tensor with the permutation of this all these Krauss operators corresponding to n channels, and this is going to act on this system of interest tensor with your control qubit, and then you will get some output state. So as I told, when you think of a completely depolarizing channel, is actually a worst case scenario when you lose all the information of the initial state, and that gets replaced by a maximally mixed state. But if you have superposition of different order, which we call independent causal order of these depolarizing channels, then you get a quantum advantage. But you will see at the end that you don't get the perfect communication, but nevertheless there is finite non-zero communication happening. Okay, so you can represent this completely depolarizing channel using the Krauss elements. They look like this. Suppose you are dealing with a d-dimensional quantum state. This channel you can represent with this kind of Krauss operators. Okay, so each of these Krauss operators are essentially 1 over square root of d times this ui, and the mapping looks like this. And this ui essentially d cross d unitary operator, and they satisfy this orthogonality condition. And if you have this completely depolarizing channel, or sometimes what we call as completely randomizing channel, for a qubit, the scenario can look like this. So we have some input state, and as I told, that imagine that if the input is, if the control is 1, 1, first goes through this n1 and then goes to n2. And then if it is in 0, 0, first goes through n2, then n1. But now if control is in superposition, then it can go like this, and also it can go like this. So because of this scenario, you cannot say definitely in which order the system has gone inside. We say that it is a indefinite causal order. So we consider various combination of this n channel in cyclic and non-cyclic order. So in quantum switch, we have this factorial n number of causal order for n such channels, and we consider a situation where we have this number of superposition which is m, it can be less than n, and they can exist in cyclic order. And what we notice is, even with this, we see that there is some enhancement which is substantial. For example, if you would consider n equal to 3, there can be possible total, total number of 6 possible choices you can have. So suppose you have channel, say ijk or 1, 2, 3, then you can have this kind of order, and then you can analyze okay, so with noisy channel, you see what happens. So you have the control state rho C, and you have the input system state, which is in the state rho, and the quantum switch is going to act on this rho C tensor rho, and this is your CP2P map. So for n such channel with m superposition orders, causal orders, you can have the input that gets mapped to output, which looks like this: 1 over m I tensor I by d plus this kind of thing. Okay. So with this output state, you can find out how much classical capacity you can achieve. That is how much classical information you can send through this energy channel. So the classical capacity of quantum channel is defined as the maximum amount of information that you can send through this quantum communication channel. That is, in this case, n such depolarizing channel. And we know that classical capacity of this channel is essentially your whole over quantity, which is defined like this. And in this paper, we have found analytically what this quantity is for n such channel. So the classical capacity of n completely depolarizing channel in this quantum superposition or quantum switch is essentially given by log d plus h into rho tilde minus h of rho m minimum. And what is this rho m tilde? Rho c m tilde. This is essentially the reduced state of the control qubit of the evolution, and this h mean is the minimum entropy of the state rho c tilde m. And if you carry out the long calculation, so we find the result for d equal to 2, and for arbitrary m, we find that this looks like this. And here is the figure which plots this available quantity versus this d, okay, for various values of m. So you see that how this available quantity is going to change with the number of order of channels, okay. So if you superpose m different orders of different channels, then as m increases for large value of m, we find that the hollow quantity for a system like qubit, you can achieve at best 0.311 bits per transmission. So even though our initial hope was that by increasing the quantum superposition, that is order of channels and number of channels, you might be able to achieve more and more capacity, but this is not true. This is not going to happen. So it is saturated to this universal value, which is 0.311. And here we plot the hollow quantity for a different number of m and dimension d. So it shows that higher classical communication is achieved for lower d, but for higher m. And if you fix the dimension, that is the qubit system, the hollow quantity increases as you increase m, but this approaches, as I said, this constant value 0.311. So, so one might have imagined that this whatever advantage you are getting due to this, superposition of different channels, and that is happening due to your control qubit, because control qubit was in superposition of 0 plus 1. So you might imagine that if you have different more and more order of superposition, then you may be able to achieve more and more communication rate, but it is not true. So it reaches actually this kind of value. So just to summarize what I said, we try to describe this superposition not only for physical systems but also for the physical processes. That is, you can have a scenario where you can superpose different channels using this control qubit or control system, and that leads to the idea, the notion of indefinite causal order or quantum switch. And over the last couple of years, several work have suggested that this indefinite causal order is actually resource. Like you can fight noisy channels, you can improve the teleportation fidelity, you can design thermal machine and so on. And also Chiriwala group, they have shown that you can enhance the communication. You can send non-zero classical communication if you use 2 channels. But what we have shown is that if you have more and more number of channels, you can still send non-zero classical information, but you're not able to go beyond the fixed value. So our result shows that the hollow quantity with how that behaves with the number of channels, and also how it behaves with dimension D. And what we find is that if you increase the number of channels, if you increase the number of orders of the channel M in this cyclically permuted completely depolarizing channel, the communication rate increases. But as you increase the dimension D, the communication rate decreases. And also we try to illustrate this behavior of the classical communication capacity with respect to dimension. And we notice that it decreases. And this most important message that I would like to convey here is that for qubit system, even if you increase the number of order of the channel, that is more and more superposition of different channels, does not increase or doesn't give a perfect communication rate. You just get saturated with this value, that is 0.0311 bits per single system transmission. Okay, so that I am almost done. So thank you for your attention.
Thank you, Arun. Any question?
Hello, sir.
Yeah.
There are a couple of questions in the chat. Can you see them?
I have to stop sharing.
There are a couple of questions in the chat.
So I think I have to stop sharing my screen, I think. Chat. Okay, now I see. Yeah. I see only one question. No, I don't see any question.
Okay. No, yeah, I think that was from the last session. Okay. Sorry.
Is there any question?
Yeah, Devashish, I have a question for Arun.
Okay.
See, Arun, this indefinite causal order, is it, like more like an arrangement kind of thing, or is it at a fundamental level?
It is what? I did not get.
For example, at a fundamental level, this causal ordering, can one sort of probe this through, a channel kind of approach? Because, causality is one of the...
Yeah. I mean, you you generalize the notion of superposition to physical processes. So that is something fundamental new insight that people are trying to play with, So all the time over the last 100 years or so, we have been thinking of only superposing quantum states, So, but physical processes, we never thought of having some kind of superposition. But now it is possible with this kind of setting, you can superpose different channel, you can superpose different, configuration and so on. I would say this is a fundamentally new insight, a new paradigm, which is not much explored. I mean, but lot of things are happening. So.
Okay. Yeah. Thank you.
So, Arun, I have a question.
Yes.
Okay. What you have observed that this Fourier quantity is limited by 0.311. Okay. Physical reason that it doesn't go beyond this value.
Yeah, we don't have a clear understanding why that is getting saturated, but most likely, the initial idea was this coherence of the control qubit might increase this communication capacity, but that is not happening because you see the maximum capacity for two channels with superposition of two different states like 0 and 1 was kind of maximum. So we thought, okay, so if you can increase this number of channel with the number of superposition also, okay, so maybe something extra will happen, but it's not happening. So even though coherence is playing a role, but somehow that is not able to beat the complete noise, So noise is still there. So
okay.
Yeah.
Okay. Is there any other question? If there is no other question, then we thank the speaker.
Okay.
Arun, again.
Thank you. Yeah.
Okay. Sorry. Oh, Kumar, you have a question? So, Richard, will you want to? Is there any other question from the audience?
To be a question in the chat.
Arun, you see the any other question in the chat box?
Let me check that. Where is that? Let me.
It's at the bottom right of your screen. There's something called chat. Bottom right.
Can quantum random work is somehow related to quantum communication? Random walk is a kind of superposition of going this way or that way to left or right, but that is not exactly quantum switch kind of scenario. That is kind of more like coherent control of coherent control of unitary kind of thing.
Okay.
Yeah.
Okay. Thanks, Arun.
Yeah.
So, Richard, can you start from this time because it is now only 7.
Yes, I.
Okay. So, Professor Richard Mackenzie is a professor in the Department of Physics, University of Montreal. He is a very renowned professor there. He received his PhD from University of California, Santa Barbara, and he has postdoc done in University of California, Santa Barbara, then Cambridge University, Ohio University, and many other places. So he got many research awards and teaching awards also. He's a very good teacher also, as well as researcher. He is actually in all parts of quantum theory, he is doing research. So I invite him to present his lecture. His lecture is on qubits as edge state detectors, illustration using the SSH modeling. Okay, Richard, you can start now.
Okay, thank you very much. I'm flattered by the introduction. I was wondering who you were speaking about. Okay, anyways, I assume you can see my screen. And do you see just my talk, or do you see a little window with the web?
I can see your slide.
Okay.
Your slide is perfectly visible. Okay.
Okay, thank you. All right, so thanks for the invitation to give the talk here. I should say. I wish I could have shown up in person, but life doesn't work that way these days. So I will speak about, now I'm having the same trouble. There we go. Okay, so I'll speak about some work that I've done in collaboration with a number of people. These people here, names in italics are students. And I have at the bottom of the screen the funding sources for this work, so thanks to them. So I'll be talking about using a qubit as a detector for interesting states of certain systems. And I'll basically use an illustration of the idea with a sort of a toy model, but a model that has interesting physical applications as well, known as the SSH model for Schrieffer-Heeger. So as a way of introduction, I'll just remind everyone that the two-level system is the most elementary quantum system that's not completely trivial. And in spite of its simplicity, it's a very important system. Many systems in physics are two-level systems. Spin a half particle can be spin up or down. Photons can have two polarizations. Many atoms, it's a good approximation to consider just the ground state and an excited state. So you get a so-called two-level atom, which is then a two-state system. Quantum dots, empty or full, and several other slightly more esoteric examples at the bottom of the screen. So I'll call these things two-level systems. Eventually, I'll also refer to a double dot, which basically is the same thing. Redundant notation I should have gotten rid of probably. Now, the two-level system, as you all know, anyone who's at this conference surely knows, is the building block of quantum computers. So they've taken on even more importance over the last couple of decades than they had previously. Okay, an isolated two-level system, as any quantum system, will evolve unitarily. So if a two-level system is in a pure state, it remains in a pure state, and it would, as a rule, oscillate between the two states, 1, 0, and 0, 1, assuming the two states are coupled. In reality, no state is isolated, and so the two-level system would interact with its environment, and this gives rise to very interesting effects and rather complicating effects. A pure state becomes an entangled state or a mixed state. We heard all about entanglement from several of the previous speakers. From the point of view of the two-level system, going from a separated state to a mixed state or an entangled state appears as a loss of coherence. So it goes from just from the point of view of the two-level system, it goes from a pure state to a mixed state. The particle from the pure level, a two-level system interacting with environment can also have a particle can escape to the environment. So from the point of view of the two-level system, probability is not conserved. And these are bad effects generally. It's no surprise, I guess, if you lose the quantumness of a quantum system, you lose the advantages that quantum mechanics can afford for instance, quantum communication or quantum computing. What I'll be studying in this talk is a system, for the most of the talk, a system composed of 3 parts. The SSH chain, we imagine, is the system we would like to understand. And I will connect the SS chain on the one side to an infinite, semi-infinite lead, and on the other side to a double dot. And the sort of way of viewing this is that the double dot is a measuring device that is intended to find out what's going on the right edge of the SSH chain. So it'll be an edge state detector. So that's the geometry I'll consider throughout almost all of the talk. The outline of the talk, I will give a very rapid review of some of the relevant features of a 2-level system. I'll remind those of you who have seen it before and introduce to those of you who haven't the Sushri-Verheeger model. I'll discuss in the bulk of the talk the tripartite system I just showed you on the previous slide. And the main question I want to address is, does the presence of an edge state in the SSH chain have a strong effect on the decoherence of the 2-level system? And just to give away the punchline, the answer is yes. And if the answer had been no, I probably wouldn't be giving this talk, I guess. I'll conclude, if I have time at least, with some current work on the idea of scanning an edge state using the same sort of idea, and also on detecting a soliton in the SSH chain. So that's an overview of the talk. Let me jump in with just a quick reminder of a 2-level system. So a 2-level system is described by a 2x2 Hamiltonian. The most general Hermitian Hamiltonian is this, where I've written it as a 2x2 real matrix, so it's not completely general. I will define the average energy epsilon 0 and the energy separation of the system without diagonal terms delta 0. There's a little bit of terminology, unfortunately, I have to introduce because I'll be using it throughout the talk. The energies of this Hamiltonian and the energy splitting are very simple to calculate. So you just get energies given by parameters that will recur throughout the talk, lambda plus and minus. And delta is the energy splitting of the Hamiltonian, including the off-diagonal term. Now, we can define for any quantum system a Green's function, which is the energy minus the Hamiltonian, the inverse of that matrix. So here's the Green's function for the 2-level system. This is an energy-dependent object. We can take its Fourier transform to form the time-dependent Green's function. It's a very simple exercise for this, this problem, and I'll get to problems where this is a much more complicated beast in a little while. Nonetheless, for this 2x2 matrix, the Green's function, energy-dependent Green's function is the inverse of the matrix. The time-dependent Green's function is a simple Fourier transform. For instance, the 1,2 component is given by this element here, where the 2 exponential factors have time dependence as frequencies given by the energies of the Hamiltonian. Now, what good is the Green's function? I did mention that the 2-level system is the simplest system, and you can answer very elementary questions with the Green's function. You wouldn't necessarily use the Green's function to, for instance, answer this question, but we could ask ourselves for a 2-level system, if the system starts in the state 1, 0 at t equals 0, what's the probability at a later time that it's in the state 2, 0, 1? And this probability is something that you can easily calculate without a Green's function. But if you happen to have the Green's function handy, the probability is given by this quantity. So the Green's function, which actually tells you pretty much everything you could possibly want to know about any quantum system, can be used to answer even simple questions like this. Now, what does this thing look like? Well, the Green's function, the time-dependent Green's function, was given on the previous slide. So it's unsurprisingly, it's just an oscillation between the states, between probability 0 and 1. So initially, the system is in the state 1, so its probability to be in 2 is 0. And then it oscillates between being in state 2 and back in state 1. And the frequency of the oscillation is given by the energy splitting. This is completely unsurprising. If we couple the two-level system to its environment, something I'll be doing is slightly more complicated than this, and then the oscillations get damped, and this figure is actually somewhat incorrect, and I'll leave it as this little exercise for you guys to figure out why this figure is incorrect, but the oscillations from the previous slide get damped away to 0. Now, so that ends my lightning fast review of the two-level system. I will now go on to the other sort of main component of the system I want to study eventually, which is the Suess-Schrieffer-Heeger model. Suess-Schrieffer and Heeger wrote a paper on the polymer polyacetylene in the late 1970s, if I remember right. And so this paper was a rather interesting explanation of why a certain polymer is in fact a conducting polymer, whereas a naive argument would tell you that it should be an insulator. So the arena for this talk is one-dimensional polymer chains. They have many interesting features, and some of the examples are that chains can have solitons, can have fractional charge, and unusual relationships between spin and charge. I'm not going to talk in any great detail about any of these properties in this talk, however. I'll mention solitons towards the end. So the arguably most important of these polymers for the purposes of this talk would be the polymer polyacetylene, which is repeat units of CH chain. So in space, it would look something like this, one would think. Now, you probably, I suspect everyone listening knows more chemistry than I do, but what I do remember from chemistry is that carbon atoms have 4 valence electrons. You see each of these carbons here, 3 of the valence electrons are taken, 1 with a bond with the adjacent carbons, each of the adjacent carbons, and 1 with a bond with the hydrogen atom associated with each carbon. So that leaves 1 electron per carbon atom free. And so naively, one might think that it is a conductor. In fact, that's not the case. In fact, well, there are 2 layers. The naive argument is wrong, but then the corrected argument turns out to be wrong as well. So we'll see it ends up being a conductor, but the first order correction to the 0th order observation that should be a conductor is that no, it's not a conductor. And then the reason why it is, why that very naive argument is wrong is known as the Peierls instability, discovered in maybe the 1930s or something, which the result is that a one-dimensional chain with equally spaced atoms and 1 electron per atom is unstable. So that's exactly the situation I had in the previous transparency, 1 electron per atom available. So Peierls shows that there is an instability and that the energy of the system, the electronic contribution to the energy of the system reduces the overall energy in a process of dimerization, which gives rise to alternating bond lengths. So instead of the picture of the previous transparency, I have a picture that looks like this, where each pair of carbons, each carbon atom has a double bond with one neighbor and a single bond with the other neighbor. So now if we count the number of electrons shared with each carbon atom, it's 4. And so there are no electrons available for conductivity. And so the naive argument that said there's 1 electron available per carbon, therefore it's a conductor, is invalid, and the alternating single and double bonds make it an insulator. However, it's actually a conductor, and the reason it's a conductor is what was the content of the Suess-Schrieffer-Heeger paper. They observed that in this geometry of having alternating single and double bonds, you can have two configurations. The first bond, say, can be double and the second single, or the first can be single and the second double. Now, that means that you can basically just sew two such configurations together, and you get one problem area where there's a double bond, a single bond on each side of a carbon atom, or it could be a double bond on each side of a carbon atom. So this would be known as a topological defect, and it's a discrete version of the simplest version of a topological soliton, namely the kink, which is everyone who learns about topological solitons cuts their teeth by the model of a kink. So this is a physical situation where the kink model actually has some validity. Now, the SSH model is a model of a hopping Hamiltonian modeled off the single double bond business. And so the idea is that where there's a double bond, there's a carbon, two carbons are closer together, so an electron hopping on the chain can hop more easily than the single bond where the distance is longer. So the SSH model is much like the standard beginner solid state physics hopping model or tight binding model with alternating hopping parameters, however. So T1 from site 1 to 2, T2 from site 2 to 3, T1 from site 1 to 2, etc. So there's the SSH model. A surprisingly interesting model, actually, given its simplicity. And when you can combine simple and interesting, that's a very good combination. More often than not, you get complicated and not so interesting. But anyways, so I'd like to examine the solutions of the SSH model, which are, as I implied, rather interesting, it turns out. Now, the model has if we imagine an infinite chain for the moment, the model has a discrete translational symmetry by two by two lattice sites. So that suggests a slight generalization of the standard tight binding model solution, where you have on even and odd sites different amplitudes, and then from one dimer or pair of sites to the next, you have a phase. If you plug this ansatz into this Schrödinger equation, you find that it is a solution of the middle equations, all but the first and last equations, if the energy and the wave vector k, or wave number, I guess, are related by this in this manner. And this is a very straightforward generalization of what you would have for a standard tight binding model. So for any energy within a certain range, it turns out there are two energy bands for this model. For any energy in those ranges, there are two solutions with equal and opposite k, and the most general solution would be a combination of those two for that particular energy. Now, we must also solve the first and last equations if the chain is finite, and that's when things get somewhat interesting, or more interesting. The two end equations turn out to be satisfied if the wave number k and the number of sites n obey this equation. So what this tells us is that given n, there are a discrete set of solutions, discrete set of k's, and so a discrete set of energies. So it's unsurprising that an infinitely long chain would have a continuum energy, a finite sized chain would have a discrete energy. So this equation that is basically an eigenvalue equation depends on n and on the ratio of hopping parameters T1 over T2. This will be a fairly important parameter, so I'll define it as R for ratio, the ratio of the hopping parameters. Now, if we look at the solutions to this equation, it turns out I think I'm going to be a little bit short on time, so I'm going to skip over some details that are in terms of this solving the problem kind of fun, but not necessarily all that interesting to many of you probably. It turns out that the Schrödinger equation is an n dimensional matrix equation for n sites, so it has n eigenvalues. It turns out that there may be n solutions of this equation, or there may be n minus 2 solutions. And it all depends on the relationship between the parameter r, the hopping parameter ratio, and the number of sites n. And it turns out that if n is big enough, if r is big enough given n, you have a correct number of solutions. I give an example here where the parameter m, the number of pairs of sites is 2, so the number of sites is 4. And if r is large, there are 4 solutions, so you're happy, you have all the solutions you expect. But if r is sufficiently small, there are only 2 solutions, and there's a pair of solutions missing. And this is generic for any value of n. I think I'll skip a slide. I think I'll skip 2 slides. So there's the point is that there is, oh no, what happened? Oh, I don't know why that disappeared, but I'm glad it came back. Okay, can someone just confirm you still see my screen?
Yes.
Okay, thank you. Thank you very much. Okay, so depending on the ratio of hopping parameters, there are either enough solutions, you have an n, you expect n solutions, and you find n solutions of the form I gave earlier, or there could be 2 solutions too few. In other words, you expect n and you only see n minus 2 such solutions. In the latter case, which is if the hopping parameter ratio is below a certain critical value, which I probably had on a previous transparency, is n divided by n plus 2. If that's the case, then there are 2 solutions with a complex wave number. And if a real wave number has an oscillatory behavior, a complex wave number has an exponential behavior. And so this will be solutions that end up being localized on the edges of the chain, and they are so-called edge states. And the SSH model is probably the simplest model that has interesting topological behavior, such as edge states, which are very popular these days with topological insulators and whatnot. So here's a graph that shows the value of this parameter kappa, which is the imaginary part of the wave number, or you could think of it as the decay, the inverse decay length, and here is the decay length itself. So if we focus on, say, the red curve, it has a certain value of, it corresponds to n equals 8, and the decay length of these localized states varies as a function of r, the parameter, the ratio of hopping parameters. And when r gets to n divided by n plus 2, which in the case of n equals 8 would be 0.8, then the decay length goes to infinity, so you get an unbounded state. So that's this is roughly the behavior of the edge states that exist if r is sufficiently small, which depends on n. So these dotted vertical lines are the values of the critical r, which varies as a function of n. Now, the energy spectrum is fairly interesting, and I'll consider 2 cases. I think in detail the case where an example of an even value of n, and then I'll say very quickly how things change if n is odd. Now, if n is even, there's 2 regimes. One is the regime where r is sufficiently large and there are no edge states, and if r is sufficiently small, there are 2 edge states which have energies that approach 0 as r goes to 0. So the energies are very small. The gray bands here are the continuum limit energy bands, which vary as a function of T1 and T2. And if this gap between the 2 bands goes to 0 when T1 equals T2, that corresponds to the ordinary type binding model. Now, what do these states look like? Well, I'll compare one state that's in the band, so a bulk state, with a state that escapes from the bands, an edge state. So a bulk state, which would be, for instance, this state here. I hope you can all see my arrow as I'm sliding along the state. So this is, we're looking at this state, and as we vary the parameter r, which is along the horizontal axis, the state does nothing too remarkable. It's the only thing to notice is that it's appreciable in the middle everywhere. So these are states that are spread out throughout the SSH chain. The different case is an edge state. So if we look at the state that corresponds to this dotted line here, it's a state that is in the band for R large and which leaves the band for R small. And as we look at the profile of this state, as we go from R large to R small, so that's the blue dot down to the whatever yellowish circle or gold circle. The state goes from the blue dots, it's big everywhere. And when the system leaves gets into this region where the state becomes an edge state, then you see that the middle values of the state, look at, for instance, the gold points here, it goes to 0. So for sufficiently small r, the state is localized at the edges and it's big inside. So this is an example of an edge state, and edge states are signatures of interesting stuff that I won't really go into in this talk. But I want to examine what we can say about edge states, how can we find them and whatnot. Now, the previous couple of slides were n even. If n is odd, it turns out things are very slightly different, but in n even, you get either no edge states or 2 edge states, depending on the value of r. In the case where n equals odd, there is always an exact 0 energy state, and the 0 energy state is an edge state, which is on the left or right, depending on whether r is greater than or smaller than 1. So in the case of n equals 21, if r is smaller than 1, you get a left edge state, a gold state here, and if r is bigger than 1, you get a right edge state. So this is just a diagram representing these states. I'll say something about it in a minute. But the point is that when you have n even, you have either 0 or 2 edge states. The edge states are on both sides. Or when you have n odd, you have either a left or a right edge state. So those are well-known facts of the SSH model. Here's a representation of the states, energy going up, and then the colors here are a representation of how big positive and negative the state is. And the only thing that's actually useful in this diagram is to look at the states that are around energy 0. And we see that for that here we have no 0 energy states. Here we have 0 energy states that are localized both on the left and the right. Here we have one only on the right and only on the left. So the bottom 2 diagrams are n odd, the top 2 diagrams are n even. Okay, so that's sort of introduction to edge states in the SSH model. How can we detect an edge state? So one thing solid state experimentalists, I'm not one, by the way, one thing solid state experimentalists would do would be say, let's attach 2 leads to either end of the chain and attach hook it up to a battery, basically, and see what current flows. So that would give you an indication of transport, and that transport can be affected by edge states. Now, this is not a great way of examining edge states, because the resistance measured in this way would tell us perhaps something, whether we have an edge state or not, but it wouldn't tell us, wouldn't distinguish between left or right edge states, and it wouldn't tell you if you had 1 or 2. So our proposal is a slight improvement perhaps on this idea, and rather than having 2 leads connected via SSH chain, connect one end to a double dot, the other end to a lead. And what we'll do is examine the decoherence of the double dot as affected by the rest of the system. And decoherence of a double dot, I I just take my experimental colleagues' word for it that we can measure that. So okay, don't ask me how to measure it. I don't know, and it's not the sort of thing I'm likely to find out. Anyways, so here's our system. It's a 3-part system. On the left, we have a semi-infinite chain described by a very garden variety hopping tight binding model. In the middle, we have the model I mentioned earlier, tight binding model, but with alternating hopping parameters. And on the left, we have the double dot that I mentioned earlier. The Hamiltonian for this model has 3 diagonal parts that represent each of the 3 systems, and then 2 off-diagonal parts that represent just the hopping with a strength TL from the lead to the chain and TC from the chain to the double dot. But I'm saying double dot now, and I mean two-level system. I just accidentally used 2 different terminologies for the same thing. So the question I would like to address is, how do we study the effect of the lead and SSH chain on the 2-level system, which is the thing we imagine we can actually measure? So what effect do the left 2 parts of this diagram have on the right part? And we'll do that by a well-known technique of sort of in the spirit of integrating out a part of the system. So the effect of the channel and the lead, the middle and left components on the 2-level system, can be incorporated into an effective Hamiltonian for the 2-level system. So the first step will be to combine the lead and the SSH chain. So on the left of this sort of equation-y type thing, this matrix here that I'm circling with my hopefully not invisible pointer, we have the Hamiltonian for the left, the lead H infinity, and the SSH chain H SSH with a hopping parameter between the 2. And what we can do is, so this Hamiltonian is an n-dimensional matrix and an infinite dimensional matrix combined. So this is an infinite dimensional, infinite plus n if you prefer, dimensional matrix. What we do is replace the semi-infinite chain by a self-energy term, which is the upper left component of the matrix dominating the middle of your screen. So it's not that hard to see, but I'm not going to prove it, that this Hamiltonian incorporates the effect of H infinity on H SSH. So it's just amounts to modifying the 1,1 element of this matrix. The addition is called a self-energy, and it's the coupling constant squared multiplied by what's called the surface Green's function of the component of the system you're integrating out of or getting rid of, which is the lead in this case. Now, the semi-infinite lead is a very straightforward problem to solve, and it's easy to get its Green's function in. So the analytic expression for the self-energy is given by this here. Now that I've now eliminated the lead, and what I want to do is basically repeat the procedure to eliminate the SSH chain as well. So I'll go from this Hamiltonian, which is n plus 2 dimensional. I'll replace SSH infinity by another self-energy term, which is so the mathematics of it is the same. The details are different. Now I have a self-energy, which is a much more complicated object. I'll display it on the next transparency, I think. So the bottom line is that the effect of the lead and SSH chain on the double dot are incorporated by adding a self-energy to the 2-dimensional double dot Hamiltonian. And I'll refer to this from time to time as H double dot with SSH chain and semi-infinite chain incorporated in. So this kind of heavy notation. So we have to figure out what this surface Green's function is for the SSH chain plus lead. Now that I believe is not on the next transparency, but it's coming. So the effective Hamiltonian is this thing here, and yes, so the added term is proportional to the surface Green's function of the SSH chain and semi-infinite chain. And the rate of escape, once we have this Hamiltonian, the rate of escape from the two-level system, or the rate of decoherence, can be calculated fairly easily. Well, actually not that easily, but it can be calculated. Now, two transparencies of nasty math, which are probably 20 pages of calculating each or something like that. The surface Green's function turns out to be this horrific expression. There's absolutely no need to understand any detail whatsoever, but I guess at least showing it to you shows you that I did a little bit of math to, or we did a little bit of math to figure this stuff out. So this is what the surface Green's function looks like. It's ugly but calculable. And then the second little bit of complicated math is that from that we can compute the decoherence rate at least approximately, can also be displayed numerically. So we do a bit of a tricky approximation to get the decoherence rate. So tau is the decoherence time, tau inverse is the decoherence rate. And it's the minimum of two values, which are these things. Again, I'm showing you them, but I don't expect anyone to have any intuitive feel whatsoever for any of this, but this is what the expression looks like. So what I want to look at now is how the decoherence rate varies depending on various aspects of the system that we're studying. But so we're going to focus our attention on this object here, which is the decoherence rate. So if we just look at the surface Green's function, which is the imaginary part, I think, is related to the decoherence rate. Anyways, the surface Green's function in two cases looks like this. So, and the only thing I want you to point out is that in this diagram, nothing interesting is happening at e equals 0. There's no edge state on this diagram. And in this diagram, there is an edge state, and things, all hell breaks loose, as we say in the technical jargon, at e equals 0. And so this strange behavior at e equals 0 will have a very strong effect on the decoherence of the double dot. So now, again, a fair bit of work and simulation is put into these graphs, but we see as an example, if T1 is greater than T2, there's a right, so this is now blue is n odd and red is n even. So if T1 is greater than T2, there's let's see, there's a right edge state in the odd case, so that's the blue here, and the decoherence remains high as n gets large. If n is even, in this case, T1 greater than T2, there are no edge states, and so the decoherence drops off rapidly. And so all I really want to point out is that whether there is or is not an edge state on the edge where the double dot is has a huge effect on the double dot's decoherence rate. So we won't propose anything terribly realistic, but the cartoon picture is that you take your double dot, you attach it to the SSH chain and measure the decoherence of the double dot. And if the decoherence is fast or slow, that tells you that there is or is not an edge state. I think I'm probably going to be running low on time, so I'll just skip this somewhat repetitive graph, which gives you the two cases whether T1 is greater than T2 or T2 is greater than T1. No edge states, a right edge state giving high decoherence and no edge state giving low decoherence or slow decoherence. and in the other case, left plus right, so there is a right edge state giving fast decoherence, and a left edge state but not a right one giving slow decoherence. So we get a very strong signal depending on whether or not there is a right edge state. Now, so the conclusion of this work is that the measurement of the decoherence rate of a two-level system attached to an SSH chain at least, which is itself attached to an infinite long chain, can be used to probe the existence or not of an edge state on the side of the SSH chain or the channel that the two-level system was attached. This work is published in this paper here. It's available on the archive too if you don't have access to PhysLet A. And so that is the work that I have, that's completed work. And maybe the moderator could let me know how much time I have left so I can know how fast I can go with the rest of my material.
10 minutes.
10 minutes, okay, that should be fine. Thank you very much. Okay, so I want to now talk about current work that's in progress. I should use air quotes progress because things are going slowly, but that's life. So basically three conceivable generalizations that we've thought of, two of which are in progress and one of which is, perhaps we'll look at it someday. First one is connecting a two-level system not to the end of an SSH chain, but to the middle of an SS chain. And the idea would then be to imagine the two-level system can be moved along the length of the chain and explore how the edge state varies, its spatial behavior as you go along the chain. So this would be a probe of not just the existence or not of an edge state, but of the profile of the edge state. And the second extension is to imagine an SSH chain with a a soliton in the SSH chain, and again move the two-level system along the chain and detect the soliton basically. And then the third sort of crazy idea we've talked about a little bit but haven't actually got going on is to discuss models beyond the SSH model that have not dimerization of carbon, say the chain of carbon atoms, but trimerization and so on. And so maybe we'll get to that at some point. Okay, so first generalization is the edge state scanner. So rather than the diagram I had of the tripartite system a few slides ago, we imagine an SSH chain with leads on either end, and we attach a double dot not to the end, but to somewhere in the middle. And we examine the decoherence of the double dot, again, just imagining that we can measure that, and how it varies as we move the two-level system or double dot along the SSH chain. So the Hamiltonian to describe this complicated looking system is not that complicated. If we look at this matrix of matrices here, if we look at all but the top row and left column, we have H infinity, H SSH, H infinity again. So that describes the lead SSH chain and lead. So all this bottom corner is the upper row of the diagram. And then we attach the double dot to the chain by sticking in a Hamiltonian here, which is uncoupled to the rest of the system, except for a single element in an off-diagonal thing in this matrix V, which essentially connects the double dot to whichever site you want to connect it to. So depending on which of the elements here is somewhere along the bottom row, if I remember right, depending on which element is non-zero, that tells you the site along the SSH chain to which the double dot is attached. So once we have this Hamiltonian, then it's basically we can repeat the procedure I described earlier to get an effective Hamiltonian for the double dot. And so essentially replacing the lead semi-infinite chain lead system by a self-energy, which is represented in this diagram here. The full Hamiltonian on the previous slide reduces to an effective Hamiltonian for the double dot, which has the not the surface Green's function, but the NN component of the Green's function for the two leads in SSH chain. So in order to understand the behavior of the double dot connected to the chain, we need to understand this Green's function, which is a generalization of the previous one. Instead of the 1,1 component for the surface Green's function, it's the NN component. And that is, yes, in here it's a brutal calculation to figure it out, but it can be determined analytically, which is kind of nice. So kudos to my student Nicolas Delnour, who did this calculation and who came up with these expressions for 4 cases, whether the number of sites on the chain is even or odd, and whether the site to which you've attached the double dot is even or odd. So 4 ghastly expressions, which the details are not at all important, but they can be calculated, which is kind of interesting. So just rapidly going over what this implies for the behavior of the double dot attached to the SSH chain. As we move along the chain, so little n here is moving from one edge of the chain to the other edge. I think here we've probably got n equals about, capital N equals about 80, so, or n even, so I think it's 80. So what we have is edge states. R is smaller than RC, so we have an edge state on the left and on the right. And the edge states, it turns out they're confined to even or odd sites. And so if we attached the double dot to an even site, we would get one type of behavior, which is seeing, in quotation marks, the left edge state, and on even sites, it would be seeing the right edge state. And so these figures tell the contribution of the edge states to the decoherence rate. And I won't go into details, but the interesting behavior, once again, is that the presence or not of edge states has a drastic effect on the decoherence. And the width of an edge state would affect the slope of this line, basically. The drop-off of the edge state affects the drop-off of the decoherence rate. I think that's on the next slide, perhaps. No, not the next slide, coming up. So here are some other examples where n is odd and a left edge state, and n is odd and a right edge state. So the sort of what I want you to attract your attention to is these sloping diagonal lines, which show basically are a representation of the profile of the edge state. If we vary the this parameter r, that varies the width of the edge state, and you can see that the drop-off is affected greatly depending on how close r is to 1. And so you could imagine moving the double dot along the SSH chain, and as it moves along, the decoherence rate changes, and the rate at which it changes tells you information on the width of the edge state. So that's the work that's more or less completed but not yet written up on using the double dot as a detector of the profile of an edge state. And work that's much more preliminary is to use the same sort of idea as a soliton detector. I mentioned the possibility of solitons a little bit earlier, where we have a diagram like this, where the single or double single state is sewn on to the single double state, and so there's a defect in the middle seen as 2 single bonds or 2 double bonds. So in terms of a hopping model, this would be a hopping model with T1, T2 on the left and T2, T1 on the right, basically. So T2s together or 2 T1s together, which is the analog of having 2 single bonds here or 2 double bonds. So we imagine an SSH chain with a soliton somewhere, and then we can attach a, okay, so If you solve the Schrodinger equation in the presence of a soliton, you get something interesting happening at the location of the soliton. And here we have a chain of length 40, presumably, or 41, I guess, and a soliton in the middle. And so we see here that there's something crazy happening. There's a state of the SSH chain that is localized on the soliton, and then there's a state that's localized on the edges. And for other situations, there are other stuff where it's local. The states are localized at the edges and on the soliton. Nonetheless, the soliton provides a sort of a defect where edge states can accumulate or can be found. I don't know if you'd call them edge states because it's not the edge, but anyways. So the program, which is in progress, is to attach a two-level system to a site somewhere along the SSH chain and study the effect of localized solutions, whether they're actually edge states at the edges of the SSH chain or states that are localized at the interior because of the presence of a soliton. So you might imagine scanning the SSH chain and you see there is or isn't an edge state, but if you're in the middle and something crazy happens, then you could conclude that a soliton is in the middle. So I want to make a special thank you to Nicolas Delnour, whose thesis is submitted but not yet, the committee has not yet met to award him his master's, but his thesis provided all the figures for this part of my talk. So thanks to Nick for that. And that concludes my talk. I hope I didn't run over time too much. I'll just leave you with the reference for the first part of my talk, both the published reference and the archive reference. And stay tuned for future archive posting for the an update on the later work I talked about. So thank you very much.
Thank you, Richard. Any questions from the audience?
Yeah, Devashish, I have a question.
Yes.
See, Rich, these AS states without soliton, is it protected by some topology, like, for example?
Yes, they are. It's the SSH model is said to be topological, and if for a finite system, the model is topological depending on the ratio of the hopping parameters, and so there is a topological aspect to the edge states. I can't give you much more detail than that.
See, why I'm asking is because there is a result due to our Rajaramon and Bell, same John Bell. They pointed out that localized states can also exist without any kind of topological regions, and they give explicit models.
Yes.
So the decoherence particularly. So in the presence of this A states, decoherence, there is more decoherence. That is a bit counterintuitive.
Well, not so much, I would say, because what I'm assuming you're referring to is Anderson type localization. So if there are states in a system, bulk states that are localized, well, states in the middle of the system that are localized, they impede transport. And what's happening here is that the states are localized, but being localized on the edge of the chain means that they're sitting right where the double dot is attached. And so they provide a sort of an escape route for a particle in the double dot, which has a strong probability of hopping to the edge state, which is large at the edge. It's true that localization can impede decoherence, but this is an example where the localization is happening on the edges, so it doesn't have that effect.
Okay, yeah, got it.
Yeah, good question.
Any other question?
Okay. I guess I'll stop sharing my screen.
Any other question? If not,
It's too late.
we thank
Yeah,
the.
sorry, can I ask something? Hello.
Yes.
Yeah, hi. Thank you for the nice, very interesting talk. I had something like, I had a question which could be a bit silly, but I just wanted to put it across. So there are some studies in which you have these spin chains and you attach the baths at the end. And then, so you can put this heat baths or like some kind of, so the edges are open in some sense.
Yes.
And do you think like something similar can be done? Like if the edges are open and looking at how they are defacing, you can say something about whether you have a defect somewhere in the center or not.
I strongly suspect that yes, you can do something similar to that. And in fact, the purpose of the semi-infinite chain is to do something very similar to making it an open system. And instead of using a heat bath or I guess, I don't know if we call it a heat bath, but instead of using a bath, we're using a semi-infinite chain to play the same role. So I think that's a very good question, and it would be interesting to study how things change if instead of a semi-infinite chain, you had a bath.
Yeah, so I was just wondering, like, you have these numerical techniques to actually study such systems using MPS or MPOs or something like that. I was just wondering, yeah, that could be interesting, yeah. Thanks.
I think it could be. I'm not familiar with these methods, however. Thanks
Yeah,
for the question.
Any other question? If not, let us thank the speaker Richard again. Okay.
A pleasure.
Thank you. So the session is now in. Anything from the organizer side? There is any announcement or anything?
Okay, so thank you all for coming today. We'll be ending now. Thank you, Dr. Mackenzie, for your wonderful speech. We'll be ending now. And tomorrow at 12 p.m. IST, we'll be reconvening and the new session will start. So thank you all once again and good night.
Thank you.